Hello, everyone. So it's time to go online again. Thank you very much for being with us today. So this is the second day of the ESOGPT conference. I would like to thank immediately again all the speakers that joined us yesterday, and of course the speaker of today that accepted our invitation, or submitted the abstract, and today enriching our program. Today is fully dedicated to the basically the use of AI and LLM and GPT technology in astronomy. We will learn a lot about this. We will see, I'm sure, a lot of fascinating exercise and experiments. So just a very small technical, again, just to remind you the technical aspects. So this event is hosted on Zoom and live streamed on YouTube on a dedicated channel. So this means that names are spelled and faces are seen, voices are recorded, and everything will be recorded and posted on YouTube. So we value privacy. So please, if you do not agree with this, please, I ask you to kindly leave the Zoom meeting, and then you can still attend and watch for free the event on YouTube, where everything can be done anonymously. Otherwise, we are happy to have you here, of course. And people on Zoom, you are absolutely welcome to make questions. Please use the raise hand options in Zoom, and then I'm chairing the session today. I will give you the word, and I try to moderate the questions. Everyone is welcome to ask questions, of course. In line with the value that we have at ESO, of course, we like to foster and maintain a nice environment, a friendly environment where all the opinion matters. So please feel free, everyone should feel free to make questions. Don't absolutely anytime curiosity. So this is a kind of conference like the one that we're hosting today, exactly meant to explore these new adventures that are the GPT technologies that are coming to us. So with this, after this short introduction, I will stop and I will ask the first speaker of today, Maggie, if you can come. Hello, Maggie. Thank you very much for being with us again. So let me first, maybe I should stop sharing, right? And then you should be able to share your screen. Maggie is currently a research fellow of machine learning and cosmology at the University of Nottingham. So an expert in the field and is interface between AI and astronomy. And this is exactly the topic of this talk, AI in astronomy. So thank you, Maggie. You have 30 minutes, plus there will be later 5 minutes time for questions. And then, as I said, at the end, there is always the discussion session where you are very welcome to stay with us. If you do you need me to give you 5 minutes, 2 minutes, or no?
Yeah, sure.
I give you the 5.
Yeah, that would be fab.
Okay, good. Fine.
You can see my screen, okay, right?
We can see perfectly your screen. Yes.
Oh, perfect. Great. So yeah, I'm Dr. Maggie Lieu. I'm a permanent research fellow at the University of Nottingham in machine learning and cosmology. And you can also find me on YouTube as Space Mog. And I'd really like to thank the organizers for inviting me to give this talk today. And I think it came around a large part due to a talk that I gave last year in ADAS conference in Tucson, Arizona. And so a large element of what I talked about there will kind of be used here, but there will be some changes because, as we know, AI is a rapidly changing field. And what I talked about last year is like completely like novel, like completely like kind of old and basic compared to where we are now with large language models. So the basis of my talk, the kind of question that I wanted to ask was, if we're looking for astronomers, what exactly are we looking for? And I was able to come up with 3 main kind of things that encompass what an astronomer does in their day-to-day jobs. So the first was research and analysis. So formulate research ideas, things to go out and investigate, questions that we want to answer. Then collect that data, use some code to like code it up so you can create some analyses and then interpret that data. The second point was to do some kind of publication, eventually read papers in the literature, write papers, use the appropriate citations, so do a proper literature review, and then also apply for grants, or if you're sitting on a grant panel, also reading through grants and figuring out, deciphering what is good science and what's not good science. And then the last component that I came up with for an astronomer's job is communication and dissemination. So this means that we go to conferences and other universities, for example, present our research there. Maybe we're lecturing if we're in academia, teaching students, or even doing public outreach, doing public engagement, just simplifying our research and science knowledge to the general public. Okay, so what I wanted to do was I went to Kaggle, which is basically a website that kind of has loads of problems that people can tackle together. And they had a very nice data set there that I liked. It was the Sloan Digitized Sky Survey, SDSS. I think it was the latest one, 100,000 observations of astronomical sources, 17 different features. And the task to solve on Kaggle was to classify stars from galaxies and active galactic nuclei from AGM. Okay, so this is all optical data. So at the time, when I first gave the first part of this talk at ADAS, it was a room of several hundred people, but only maybe a handful had actually got ChatGPT-4. And ChatGPT-4 was already out for a couple of months already. And it was really surprising to me that no one was actually paying for it. So I was just kind of demonstrating some of the capabilities that it has. So ChatGPT-4 had at the time some plugins where you could do some data analysis. So here I was asking it I uploaded the data and wanted to see what it could do. And it talked me through each of the steps of exploring the data and then using machine learning to classify them with that task. Surprisingly, it was able to tell me that I should use a training and test data set, so splitting them appropriately. It was able to identify all the features without me specifying what those features were in the tabulated data. So it knew like what magnitudes were, etc. And then it was able to produce all of these metrics that would be, well, it trained this machine learning model. It identified a random forest classifier would be an appropriate choice. And then it did the modeling and then did the evaluation with all of these metrics that we would properly see in a person who uses machine learning in general. So like precision, recall, F1 scores, etc. And it was able to get a 97% accuracy on this this model from the data that we had. I next asked it what we can learn from this, and it went ahead and interpreted all the results. So it talked about the different importances of different classes. It talked about what features were effective at distinguishing between these classes, talked about misclassifications, and it also gave me some ideas for improvement and the robustness of the model that we looked at. So these are all like the basis of a good, or at least okay, astronomer kind of piece of work in astronomy to analyze data, I would say. So these are the summaries of the kind of things it came up with. It told me So these plots actually came from ChatGPT-4. We've got the distributions of classes, the redshift distribution, the magnitude distribution, etc. It told me that there was common misclassification between galaxies and QSOs. It told me the feature importance, redshift, is the most important, and then the different photometric bands, and then all the improvements like feature engineering, data augmentation, and hyperparameter tuning. Okay. But it turned out at the time last year, it wasn't able to do everything. So this is a plot from one of my researchers I was working at the time. It was a variational autoencoder with a transformer network based in it, and asking ChatGPT to work on like these state-of-the-art kind of methods, it wasn't able to come up with anything. It knew that it wasn't trained to that level of expertise to come up with new things or play around with new things. It's only able to do the very kind of well-explored methods like random forests and some of the more basic like methods of analyses. So ChatGPT is not the only LLM on the market. So this figure from Yang et al. 2023 is probably already outdated, but you can see how fast these different models are kind of being produced. 2018, 2019, you don't have that many models, but now we're getting models pretty much every day. Google Bard is now Google Gemini. Llama is Facebook's model. We have Bing Chat, Claude 2, I think is Claude 3 now, and a load of other different models, large language models being produced all the time. So it may be a little bit confusing at what kind of LLM model you should be using, right? And why did I use ChatGPT for? So Hugging Face has this lovely leaderboard, LMSys chatbot arena, and it compares various benchmarks to decide what is the state-of-the-art LLM model at the moment. At the moment, I think a couple of days ago, I made this presentation, and right at the top is the O1 model from OpenAI. This is the latest model from OpenAI. It's still in beta, but it's a reinforcement learning based model, which OpenAI says essentially will think before it produces content, because it creates this internal kind of conversation with itself before it will even produce any response to you. Following closely, we've got like the latest official ChatGPT 4.0, followed by O1 Mini, and then Gemini 1.5. We've got Grok from Twitter, and then a load of other models. But I think it's really important to note that all of these, even though they're in this table that tell you this is the better one over the others, it's not always a very clear cut. The scores are very close to each other, but also it will also depend on the benchmark that you're working to. So if we instead not look at overall score, but look at math, you see like a little bit of shift, like Claude jumps right up. Gemini is shifted up a little bit too. O1, the large model is kind of dropped down a little bit based on math benchmarks. And then there's coding benchmarks, there's English benchmarks, there's a load of other benchmarks that you could be looking to. So I think it's really important that you explore a load of different of these LLMs. And actually, previously, I was using both, ChatGPT, Google Gemini, and Anthropic's Claude all at the same time. And I really like using all three, because then I can compare the results of each of them and come to my own conclusions about what is right and if the content they're producing is correct or not. But earlier this year in June, I switched from paying for ChatGPT-4 to use instead Gemini Advanced. The pricing plans are similar, and Gemini Advanced has a 1-month free trial, so I would definitely suggest you check it out if you haven't already. But what I really like about Gemini Advanced is that it's integrated to many of the products that Google have and that I use on my day-to-day life. And a bonus on top of that is the 2 terabyte of storage, because I have a load of things stored on Google, sorry. So doing that kind of same task, uploading that data set that we had from Kaggle, you can do exactly the same thing. You can upload a data set to Gemini and ask it to explore the data set, and it will do this. It's also integrated with Google Drive. So if you've got more than one data set, it can look through all of that. Or if you've got multiple files, it can search through all those multiple files. So here, again, like ChatGPT, it's produced some plots. I really like that it's been able to produce this interactive plot. It's given me all the code so I can reproduce this. And then moving on from there, it's looking at some of the relationships between the magnitudes of the different sources in this data set. Now, and it's done some Pearson correlation coefficient analyses. Now, this isn't typically what would be done by an astronomer, but it does also tell you some of the potential avenues for extension. So it tells you that actually we could look at color magnitude diagrams, and actually this is something an astronomer would more typically look at. It even says, oh, you could look at using machine learning techniques to classify the objects in this data set. I didn't specifically ask it to do the task of classifying astronomical objects yet in this data set. So it's already come up with some ideas of further work. But then I asked it to remove outliers. Now, previously with ChatGPT, when I asked it to do the kind of data exploration, it automatically removed the outliers for me. But when you see what Gemini does is that it just drafts a response saying, oh yeah, maybe it could be a good idea to remove outliers, but it doesn't actually go there and do it for me, which I thought was a little bit annoying, because kind of ChatGPT just kind of knew what I wanted to do and did it, and Gemini just kind of suggested it. But the key here is that Gemini Advanced is not optimal for doing the kind of stuff that I want to do here. And this is where I move on from what I previously spoke about, if AI could replace an astronomer, yes or no, to can like LLMs help astronomers become better and enhance their kind of career profiles. So I use Google Colab quite often. So for those of you who aren't familiar, Google Colab is essentially a collaborative Jupyter notebook system that allows you to create code and do all your coding on the web. So Gemini is integrated to Google Colab, and you can see that little diamond sign in the top right-hand corner that tells you it's integrated. And I can ask it to generate code. So I can ask it to generate code. So here I'm asking it to explore the data set. And it's created all of this code. It's well commented out. It's told me exactly where I need to replace the string for the actual file name of my data set. But what I really like here is also at the top of this kind of coding sample, you can see that it says suggested code may be subject to a license, and provides the source to where it did its learning to produce all of the code that it's done. So I'm going to go ahead and replace that correct file. It's going to produce me all of those nice analyses of looking at what that data is. And now I'm going to ask it to use random forest to classify the data. And again, it's been able to import the appropriate libraries. It's identified training and testing sets to split, and it does everything, including evaluating the model. And again, at the very top, you can see all the different sources that it's been able to create this coding snippet from. So when you run that, it's created your accuracy, your precision recall, F1 scores, and even support. I also tell it to create another machine learning model without specifying exactly what method to use. And it's chosen logistic regression. It's gone ahead and done a similar kind of code snippet to produce similar kind of outputs. And you can see that with the logistic regression, you're getting 0.6% accuracy over the 0.978, which is actually higher than the ChatGPT one that we used previously. If you don't want to generate code, Gemini also does kind of like these autofill to help you predict the code that you want to write. Here it's produced some confusion matrices, receiving operating characteristic curves, and even some plots for feature importance. So you see redshift is the most important for identifying the classes here. So I really, really like using Gemini to enhance my coding. It can help you spot bugs and all sorts of things. So yeah, I think it's really made my coding more efficient and improved it. It can suggest to you how to better write your code. In terms of communicating and disseminating your research, Gemini is integrated with Google Slides, another tool that I use quite often. Again, top right-hand corner, you can see, you can just click on it to access the Gemini prompt entry. So here I'm asking it to create a slide about the use of AI in astronomy. And after a little while, it's created this beautiful slide with an appropriate title, some bullet points. If you're not happy with it, it can edit it and create a new one quite quickly. I wanted to be more specific with the prompt, and I think it's really important that if you are using LLMs, you should be very specific. In this case, I've asked it to create a slide about AI to classify galaxies and stars in SDS data, and it's created this for me. One thing I do want to mention is that I feel like the UK version of Gemini is slightly behind the US version. So it was only up to maybe 2 or 3 weeks ago that we were able to use image generation with Gemini in the UK. But in the US, they were able to use it months ago. And this was due to some EU laws. But so for this reason, I feel like Gemini UK might be slightly different from the US, and they might have a slight advantage over us. But that aside, it's created this lovely slide for me with a beautiful, appropriate image. It's even provided like a citation for me, Kosiba et al. 2020. Actually, this is a paper that I was on. And even though the text in this slide is talking about classifying stars and galaxies, this paper is about classifying galaxy clusters from AGN. So it's slightly different and maybe not the most appropriate citation in this scenario. Okay, I think I can slip that one. Google Docs, I think if you're using Gemini, it's great for Q&A, but if you want to do writing big parts of text, definitely look to Google Docs. Again, Gemini implementation here is able to create huge amounts of text, and I really like their refine tool here. So you can choose a tone, whether or not it's formal, more formal, or more casual. You can summarize text, you can bullet points, you can make bullet points, you can elaborate or shorten, or you can make a custom kind of edit to your prompt to make it more like what you want it to say. So here I've asked it to include some references. And that looks pretty good to me. Some introduction to SDSS in machine learning. Pretty great. So I don't like these bullet points, so I'm just going to ask it to make it into a more continuous form of text, not bullet points. And it's going to go ahead and do that. And you can either like replace your generated text or insert it if there's parts that you do like and don't like, so you can more tweak around with it a little bit more. Fine. Okay. So going back to the normal Gemini Advanced, I said that this worked really well with like questioning and searching. It's integrated with the web, so it can find the latest like stories and news and papers for you. But when I asked it to create a literature review, what happens? So it's come up with some good papers: Sloan Digitized Sky Survey, Stoughton 2002, Galaxy Zoo, Lintott 2008, another Galaxy Zoo 2011, and some other things. And they've explained like basically what these papers are about. Fine. Now, if you actually go and look more closely, you'll find that, okay, the SDSS early data release citation is correct. The Galaxy Zoo one is kind of correct. The title was slightly skewed for the 2008, but the 2011 one didn't exist at all and had this exact title. The network, neural networks in astronomy, Baylor and Jones, does not exist. And the photometric redshifts and their applications in astronomy and cosmology, again, does not exist, unfortunately. And this isn't anything new. This is really, really bad. It's a huge problem. And I'm an editor for Astronomy and Computing Journal. And actually, just this week, I got this email from one of my reviewers on a paper that I was journal editor for, and say the important thing here is that the authors are citing a paper that does not exist. This was the second round of review. So they'd already missed this missing paper in the first round. And then shortly after, the second reviewer came back saying, okay, we can't find this citation. And then these two other citations seem to be incorrect as well. Responsible AI is so important. We allow the use of AI in our journals, but it's really important to provide transparency to the general public that there has been AI technology used in these processes. And we require people to put a statement to say they've used AI, how it's being used. I mean, we have so much to gain from this AI. People can be put on a fair playing field for translation, improving your grammar and writing. But it's really important that we don't use AI to produce scientific results, because that's not you doing the work. Misinformation and disinformation is not new. It's been around forever. Take, for example, this tweet from the Flat Earth Society. Have you ever heard of electromagnetic acceleration or bendy light? It's a fascinating concept that could explain why the Earth appears curved when it's actually flat. Yeah, thank you. And there's a whole trail of this tweet, and it sounds very compelling, just like LLMs. LLMs can create compelling, context-aware content, so they can trick you. It's important to be aware of this limitation and critically evaluate it before using it as a black box, I would say. Hallucination is when your model creates unfaithful, fake, fabricated, inconsistent content. Why do they hallucinate? Well, typically it's limited training data. We don't have access to every question and every answer in the universe. LLMs are not conscious. They're not really understanding things. They're looking for pattern recognition. So they're only producing things that are likely to be true. And this will lead to biases and errors, because there's biases and errors and all of that fake news existing on the internet. There's also a study by Gekman et al. In 2024, so a recent paper, that showed that if you're fine-tuning pre-trained LLM models, it can actually increase hallucinations. And I feel like this is kind of the route that we are going already. A lot of fine-tuning, especially even in our own fields, there are fine-tuning ChatGPT models specifically for astronomy. So care should be taken when taking this approach. Prompt engineering, I already mentioned this earlier, but if you've got garbage coming in, you're going to have garbage coming out. Your output quality is directly dependent on the input quality. So if you're going to put a vague, ambiguous, incorrect input, expect the same kind of outputs. And to minimize the amount of bias and hallucination, you should provide clear context, clear constraints. And this is even more important if you want to kind of avoid harmful content. Prompt engineering is an iterative process, so it might take several attempts trying to make clearer what you're trying to say to get the outputs that are actually worth using. In 2024, Google's environmental report showed that the carbon emissions and things like that has a huge impact on the climate due to AI use. In 2023, their electricity consumption grew by 17%. Their greenhouse gases increased by 13%, which is equivalent to 38 gas-fired power plants. And to put it into context, GPT-4 took 100 days to train, 50 gigawatt hours, which is equivalent to the energy usage of 5,000 households per year. So it's insane that we're spitting out so many LLMs all the time to achieve what, I don't know, is very similar to each other. And these small incremental changes. There's also a fear of over-reliance and dependence on LLMs, and this can lead to decrease in critical thinking and human judgment. There is the allure of this seamless efficiency, but it's also important that we do retain some human expertise and prevent automation bias. A huge thing that is important to me is mode collapse. As the internet is using more and more AI, everything on the internet is going to be produced by AI. So it's going to be training on itself, and eventually all the content will be AI produced. We have a responsibility to take that into account when we're using AI all the time. And then lastly, I want you to think about quality and not quantity. There are, if you imagine like a bakery, there are these like factories that are producing great loads, high quantities of cakes. They look very kind of beautiful, etc. But we still go to the kind of boutique patisseries because we just know that they're better. So it's not always LLMs will be creating that better content. There are going to be bespoke people with that expertise that machines and high productions cannot produce. Overall, if you're using an LLM as astronomer, beware to be transparent, think about diversity and inclusion, continuous monitoring and evaluation of your outputs from your LLM, be educated about the limitations and risks, and also the ethical guidelines. So overall, just be mindful and demure. And then going back to that initial question that I asked, can AI take your job as an astronomer? Thankfully, when I asked Gemini, he said, sorry, I'm not an expert in astronomy. So he can help you become a better astronomer, but hopefully he won't take the best of us in our jobs. Thank you for listening, and I'll take any questions.
Thank you very much, Maggie, for the very, very fascinating, interesting talk. Fascinating and scary at the same time. so much, but you raised a lot of very, very important questions, actually. So thank you very much for that. Okay, so I have now, there is time for some questions. I think I saw a hand raised, but I kind of lost it. So, okay, I see Fabio. Yes, please, Fabio.
You hear me?
Yes, we can hear you.
Okay, I was very surprised to hear that Gemini hallucinates so much, especially about links and documents, since it claims it has access to the internet and so potentially can verify these links. You mentioned prompt engineering. I was wondering whether you could avoid this, so asking explicitly to cross-check the links, for example. But the other question, I'm a software developer here at ESO. Would it be helpful a programmatic interface where that, for example, sends the prompts and analyze the response, for example, checking these links, and eventually, in case, send another prompt saying, hey, these links don't exist. So something like that.
Yes, absolutely. And that's why I said it is a very iterative process. When I was using ChatGPT-4, it had Scholar AI integrated. So that was linked directly to the archive. And I found those results were pretty much always accurate. With Gemini, you can ask it to provide links, and sometimes those links will work, and then sometimes it will just say, oh, that link doesn't work, so it's a fake link. So there is that problem. But I use Google Scholar, and right now Google Scholar doesn't have Gemini integrated, but I'm sure like eventually it will integrate Gemini and improve for citations for sure.
So it will reduce this problem. So
yeah,
you will always
absolutely.
have hallucinations, but less, you mean?
Yeah, because it will be targeted, it will be integrated specifically. So for the Colab example, I showed the coding in Colab was so much better than the standard Gemini prompt thing, and because it's tailored specifically for coding, and it will produce sources like where it got its coding information from, and largely it is GitHub links. And then for the production of the Google slides, again, it does provide the source where it's got those all its information from, and what's it trained on. So I'm sure once they integrate Gemini into Google Scholar, it will be able to be more specifically tailored for finding correct references. But right now they don't have that.
Yes. Thanks.
Thanks.
Okay, thank you very much. And we have the second question, and then we can move on. So this is Maya. Please, Maya, you can take over.
Yes, hello. Hi, it's nighttime here, so my camera quality is not very good because we don't have time for that. But just follow up on the last question is that there are the techniques that do that, and some models do perform better by using retrieval augmented generation, for example. So just opening a discussion for later, maybe some researchers do seem to like Perplexity a lot, and I believe it does use retrieval augmented generation to just provide links. So maybe that could also, I just wanted to chime in a bit. So not that much of a question, but rather some, sorry, not maybe suggestion, but yes, Perplexity has been working pretty well for me regarding not hallucinating that much. So it does seem to get a bit better.
Thanks, Maya. I've been using Perplexity a lot. I really like their news recommendations, actually. But other than that, I haven't explored using it very much for any of the other things. But I'll be sure to check it out, and I'm sure people watching and listening will too.
Yeah, I do have a Pro version, so I don't know how as the free one perform, but the Pro seems to be quite grounded, sometimes a little bit outdated, but I didn't catch it hallucinating yet. So thanks for the great talk.
Thank you.
Thank you, Maya and Maggie. Thank you very much for the talk. As I said, so we can now move to the contributor talks, to the first contributor talk. Maya, if you're of course invited to stay with us, and as we will have the discussion session later. But now let's move again to Marcos. I guess it's going to be you're going to share the talk, right?
Yes.
Okay,
yeah.
fantastic.
So let me.
Still, there are 50. So it's basically you can start now. I can give you. I don't know. I guess you can self-regulate, right? The talk in a sense.
I cannot share the screen. It says that the host disabled.
Yes. Give me a second. I give you immediately the. Okay. Now, try again.
Yep.
Fantastic. Yes, we see the screen.
Okay. Can you see my presentation in?
Yes, in presentation.
Okay. So Miguel, doctor, my colleague, he's also connected, and both of us will be doing this presentation. So let me start. Thank you very much, Giacomo, and the organizing team for the opportunity to present this work. So together with my colleague, Miguel, doctor, we will be presenting this work on ESASky, AI capabilities, and the work that we've been doing with LLMs. And we are presenting this work on behalf of the ESASky team on the ISAC Science Data Center, the Programmatic IT team, and the Data Science team here at ISAC in Madrid. So let me start. So here at ISAC, in the ISAC Science Data Center, we host the archives from the ISA's astronomy, planetary, and heliophysics missions. And the amount of data that we host is growing exponentially, and it will grow even larger when the full of Euclid data is here. So here in the data science and archives team, we are always exploring ways to facilitate the archival data discovery. And in particular, we've been working for several years on the development of ESASky. That is a really innovative tool that many people are using already for their work. So in this presentation, we will show how users can interact with ESASky via our chatbot that is using natural language processing. And also we will show another research and development project that we are doing in coordination with the data science team to enhance the EVA-bot with LLM and RAG. So ESASky, for those of you who don't know, you can access it in sky.isa.int. It's a multi-wavelength, multi-mission, and multi-messenger portal that we developed here in Madrid. It gives access to about 100 missions, data and metadata, thousands of catalogs, HIPS images, taking advantage of the IBO protocols and all the work that many people are doing in other data centers, and particularly in the CDS in Strasbourg Observatory. So it's driven by scientific use cases and the needs from the community, and it gives real-time access to the main astronomical data centers in the world, not only ours. You can access ESASky via our JupyterLab widget, via AstroQuery and table access protocols. But what we wanted to show you here is the EVA-bot and the things that it's doing. So this is part of a project that started several years ago, and now let me go through a quick demo of the bot. So when you enter into ESASky, sky.isa.int, you can just browse the contents of the application, but then you can also go to the bot, and then when you enter the bot, you get some suggestions on how to navigate the ESASky application, but you can also just ask whatever you want, and if your question is not related to the contents that we have in ESASky, it will just not work. So, for example, if you ask what is a spiral galaxy, it will give you some general description. And then if you ask, okay, show me an example of a spiral galaxy, it will trigger the opening of one of our pre-computed list of spiral galaxies that is mostly for outreach purposes, if you like. But it can navigate this list you can play, you can pause the list or close everything altogether. Then if you just want to go to a particular object, you just type in the name, and then the ESASky sphere recenters into those coordinates. You can zoom in and zoom out. Here I'm just saying, okay, zoom in to 0.5 degrees of field of view, and then this is what you get. And then you can also change the background images. Here I'm switching from the DSS2 color in the optical to the ultraviolet. So it's giving me the what are the options that are available. So it's showing me, okay, you can use GALEX or XMM UV. So I was switching to GALEX. And now, for example, if I want to see, okay, what are the observations available in this field of view for the various missions that we curate? So it gives you this list, and then very easily you can just get for this particular region of the sky just by clicking on the number of the menu. You just get all the footprints and metadata for, in this case, for Herschel, Spitzer, and ALMA. And then now I want to overlay some catalog data. So again, I say, okay, what's available in this region of the sky? And then, so these are all the catalogs that that are curated in ESASky. And then it just gives you this just by typing in or talking to the bot. You can also talk to the bot, which can be convenient for some people. You just get the overlay of all these catalogs. And now, if you want to change the background image again from what we had before to another wavelength, this is possible. When you enter into a conversation, you ask for things maybe related to images or maybe related to catalogs, but then typically you need to exit the conversation so that the bot knows that you are asking for other things. So if I want to add to my stack of background images an optical HIPS image, then I need to exit by typing help and then asking to add another image in the sky. So on top of the ultraviolet, I added again the DSS2, and now I want to add an infrared HIPS. So I have all these options, and I'm going to choose one, the number 4, which is the Hasselblad RGB at 70 and 160 microns. And then with the player, I can again navigate across wavelengths for this particular object in the sky. And essentially, you can do almost everything that can be done in ESASky via the application. Let me move a bit forward. Then we have you can also operate the outreach area of ESASky, where we have data, where we have outreach images from JWST, Hubble, and Euclid, which can be very convenient because being pretty images, they also have quite a lot of science encoded in those images. So it's useful to be able to play this transparency game between the actual background images that are like the actual data, and on top of it, the outreach images that have been created by the various research institutions. Then since I mentioned that ESASky is also multi-messenger, so it also gives you the possibility to overlay the probability contours for the various gravitational wave events that have been produced by the LIGO Virgo Kagra collaboration. So we are listening to events. So every time a new event is announced by their alert system, within 30 seconds we get the information from the alert system, we ingest it into our databases, and we make it available, so that the people can access all these gravitational alerts almost in real time, and then take advantage of the multi-wavelength information that we have for all these catalogs and observations to go to a particular region of the sky and maybe try to identify electromagnetic counterparts for follow-up observations from the ground. So now, that's going a bit into the LLM part, or which is this research and development proof of concept that we are working on. So the scientific questions that we want to address here is, what if we could ask ESASky to find observations, catalog, or spectra for specific types of objects in a given region of the sky, for example, a black hole or an AGN, or you name it. So then if the object information for a particular object is already available in the metadata from our archives, or it's in SIMBAD, then this can be done with existing tools. But we all know that object classification is not straightforward, and very frequently, this information is not available. So what we are trying to do here is to use LLM and RAG to infer to some extent this information out of the titles and abstracts from the scientific publications that for objects for which that have been mentioned in a particular region of the sky by someone in the community. And now I will let my colleague Miguel go a bit into the details of this.
Thank you, Marcos. Good afternoon, everyone. Well, now that we have seen how EVA in general and EVA bots for ESASky in particular can be used to operate fairly complex systems like ESASky, I think it's worth it to briefly introduce EVA platform itself. EVA stands for ESA Virtual Assistant, and it's a web system that allows ESA community to create, train, deploy, operate, monitor machine learning powered bots. Okay, it runs totally on ESA premises, and it supports a wide variety of technologies ranging from graph-directed bots, state machine bots, to large language model powered bots. So in the next slide, we can see how ESASky bot looks like. In particular, we can see the bot that we have been used to operate ESASky. So for this bot, we decided to approach the development using a machine learning state graph-directed bot. So we can shape the dialog flow of the bot according to the states of the application we are trying to operate. So this is a very powerful approach. However, this technology, directed graph, it doesn't allow us to approach the problem triggered by Marcos, the scientific question that started all this research. So we need, for address this problem, we need a higher level of understanding capabilities. We need to somehow infer knowledge when processing titles and abstracts. So that's why we said, okay, we need to incorporate a higher level of understanding capabilities to our ESASky bot. So yeah, we decided to use large language model, and we decided to back our bot with a Mistral 7B model. So yeah, in this slide, we can discuss why the large language model technology is the chosen technology for addressing our problem. As we can see in the slide, large language model offers several features and capabilities, but we are going to focus on the 4 features listed there. So as we can see, large language models are very good zero-shot classifiers if used properly. That means that we need to be careful when with the way or the words we use when we ask the model or the bot. So in this way, or in this particular case, prompt engineering plays a crucial role. Okay, so the second one, large language models are few-shot learners. So we can instruct the large language model to process and return the information in a specific way or in a specific format. Okay, also, this is also key. Prompt engineering is also key. We want to exercise these capabilities. So next, large language models are good data extractors. Depending on the data source, retrieval augmented generation is key here, because if the way is the only way we have to provide domain-specific knowledge to our bot. So talking about tabular data requires transformation and some other techniques that we are not going to discuss here because they are somehow out of the scope. So finally, large language models extend capabilities with use of tool use or tool calling, which is the way that we have to exchange information and to use our bot to in order to address complex systems by collaborating with external systems or applications. So yeah, that is the reasons why we decided to use large language models to address our problem. And these 2 techniques, prompt engineering and retrieval augmented generation, are the ones we are going to apply. So yeah, let's move on to our experimentation. Yeah, so we can see here the EDQL query that we use to extract the data set that we use for testing and validating our approach from Sinbad. And this is how it looks like. So if we go to the next slide, we can see what we did actually. So first, we tried with zero-shot prompting. Here we got poor results, and we get some hallucinations in the form of output format or inexistent requested coordinates. So okay, it was okay. We get some data in return, but we decided to move forward or to move on to the next approach, which is few-shot prompting. Here we got better results. We fixed the problem with wrong output, but still the classification of the entries is not good enough, which is in line with our expectations, because the bot that we created and the model that we are using, Mistral 7B, as I said before, doesn't have domain-specific knowledge about astronomy. And this is the knowledge you need in order to properly extract astronomy information from the titles and the abstracts retrieved from Sinbad. So then we decided to apply the following architecture, which is a retrieval augmented generation two-step pipeline architecture. So in the next slide, we can see the architecture that we actually implemented. So we provide our large language model with domain-specific knowledge along with the SIMBAD data tables. Okay, this is the solid line that you can see on top of the diagram. So we took all this information and stored it in a vector database in order to provide context to our operation. So then the user make a question about a specific prompt category, and this prompt that the user is using to trigger the process is actually combined with the context and with the prompting template manager that we are using for classifying the entries. So then all this information is sent to the large language model. It returns a list of actually labeled entries, and then all this information goes back to another template manager where all this information is combined and sent to the large language model again as a second stage, so we can actually retrieve the coordinates of the objects identified by the large language models. So yeah, this is pretty much what we implemented. There you can see the prompts we use for each of the stages, just in case you want to try to reproduce our results. Yeah, let's see in the next slide the results that we got. So as we can see, we get an enhancement by using our architecture. So we got better accuracy, and we found objects that making use of prompting with few shot or zero shot, the model was not capable to infer. So yeah, I mean, we are aware that we use a relatively small data set, but yeah, this is a proof of concept, and we are just trying to validate our approach prior to decide if we need to move on to a more operation-ready system. So now, now we have explained this a bit. So let's see how it works. So here we see that we are in a specific area of the sky, of ESASky, and then we just query our bot about a specific prompt category. In this particular case, EGN is the one we have chosen, and we said, okay, we are here in this area of the sky, so please check SIMBAD in this area and parts next to this area in order to see if you can find some kind of publication where titles and abstract are somehow related to EGN. Okay, so here we can see, of course, we are working with a small data set, so we are not actually querying the whole possibilities provided by SIMBAD, but this is the small data set that we are working on, and yeah, we actually identify, and we can see there how two entries have been found from SIMBAD tables. Now we ask our IVA bot to navigate to the coordinates already listed in the answer. So it takes a bit because it needs to process the coordinates, and then the bot requests the information that the large language model has returned, like the right ascension and the declination. So we just need to reply the bot, providing the required information, and it will automatically move the focus to the specific point that has been provided by the bot. So yeah, it's moving. So yeah, it already made the movement. It went to the specific part, and there, in this point, we can see if actually there is a publication that is talking about the topic that we are asking for. So by filtering in the menu, we can see that, yeah, indeed, the publication suggested by the large language model is actually the one that ESASky has retrieved from the catalogs, which means that even though the word or AGN is not explicitly indicated in the title, nor explicitly indicated in the abstract, but the large language model is able to infer that this publication is talking about it. So then it can suggest it to the user in case, like happened, the user wants to actually find or get some suggestions about a specific topic in a specific part of the sky. So yeah, that is the work we have been doing for these years. Yeah, let's see the conclusions and the takeaways from this presentation. First, at the Data Science and Archive Division at ESAC, we are continuously working, trying to find new ways to facilitate access to astronomical data. And this ESASky and EVABot project is one of them. There are several groups, as Marcos indicated at the beginning of the presentation, involved in this experiment and with other activities. And what we presented here is just a proof of concept, okay, that relies on retrieval augmented generation to reduce hallucination, even though it's not totally removed. So if we continue working on this, we will try to move on to the agentic patterns in order to improve the results on this matter. And finally, yeah, this is a proof of concept. So this is not on production, it's in our acceptance environment. So far, we managed to keep the response times and their acceptable levels. However, if at some point we decide to scale up this system, this feature, we need to reconsider both the architecture of the RAG along with the architecture of the system. Yeah, and this is pretty much all we wanted to share with you all. So yeah, thank you for listening, and I don't know if
thank you very much. Thank you, Miguel and Marcus. We are a bit super fantastic, really, very beautiful. There is one hand raised, so we can have one question from Dario, and then who was the first one who raised the hand, and then we move to the next speaker. But Miguel and Marcus, if you can stay during the discussion, we will have more questions, so we can keep on discussing. So, Dario, please.
Hi, Dario, working in ESO. The question is about this model that you used and the data. Seems to me quite a lot of work. And the previous presentation talked about how much it costs in terms of energy and also in terms of resources. Do you think you can scale up in the future for something more usable, or you stay at the experimentation level?
Well, I mean, I will try to thank you for the question. I will try to answer the technical level about if we are going to actually put this on production or not. It's something that I will leave to Marcus to reply. But I mean, in terms of yeah, we are using resources from our premises. Okay, so we have a cluster, a Kubernetes managed cluster, and we are using right now for this experiment, we are using several CPUs and a considerably amount of RAM. But we actually think that we have a way to improve, and we can actually address the problem in a higher level by making use or incorporating GPU's capabilities to our environment. So this is something that is under the discussion. We have a lot of teams involved on this. But yeah, I mean, since we are not accessing external resources, we don't have to somehow directly pay for it. Yeah, we think that we can, from the technical point of view, we can actually approach a higher level of capabilities if we come to, to make not just research and development, but also operational performance. Yeah.
Yeah, if I may just add a sentence on this. So I don't think that really resources is an issue. I think the main issue for putting all of this in production is that the ESASky is starting to be a well-established tool that is recognized by the community, and we don't want to make any mistake or let it like hallucinate or give like some really ugly feedback just because someone managed to trick it. So the reputation of the application is at the moment the priority. So we will continue working on these proof of concepts, and we will continue presenting them in the relevant forum. But for the moment, it's unclear whether we will put exactly this in production, just because of the other things that are like floating around the LLM technologies. Yeah.
Okay. Thank you very much. Thank you. I'm sorry, there is still one hand raised, but Miguel, we need to move on. And I ask you kindly to be patient. If you can keep the question for later, of course, that will be fantastic. In the meantime, let me thank Marcus and Miguel again. And then Nolan, yes, please. I see you already. You can already start sharing the screen so we can move to the next talk. Gravity Bench, a benchmark for an AI astronomer.
Great. Yeah. Can you guys see it?
Yes, perfectly.
Okay. Awesome. Whoops, I can't move back. There we go. All right. So hi, everybody. I'm Nolan Koblischke. I'm a PhD student at the University of Toronto. And today I'm going to be presenting Gravity Bench, which is a benchmark we developed for an AI astronomer. Current benchmarks that evaluate these models on their understanding, they typically consist of multiple choice questions, and which is good for testing their factual knowledge. But as astronomers, most of the time we spend is really coding a lot of the time. And so we really wanted to develop a benchmark that could test how well these models could solve astrophysics problems with code. And if we show that they can do this really well in the future, you can start thinking about some exciting possibilities, like a coding assistant for astronomers. This already kind of exists with like GitHub Copilot, and it allows us to spend more time on the science and less time debugging, which is really great. But if we show that these models can, develop research grade code, then you can really start thinking about an exciting future where you have these like AI research systems where you provide data and an idea, and then they go off and make plots, analyze it, and then generate a report for you. This is kind of like an AI grad student, but don't get an existential crisis, grad students, because I see our future as, having a team of these agents working on the technical stuff so that we can focus on the bigger scientific problems. And I think this kind of system would really accelerate science. But let's zoom out and see our progress towards that. So this is really like the first 4 years of language models, I would say, large language models. In 2020, GPT-3 came out, and I was lucky enough to be like to get beta access when I was in the public beta. I was in undergrad at the time, and I was thinking, okay, would this be useful for my physics homework? But it, at the time, couldn't even make a tuna sandwich. So yeah, it's kind of forgetting the bread, which is kind of an important part, in my opinion. So physics problems was just a crazy dream. But now, 4 years later, I made a whole project about it. And so we've gone a long way. 2 years after that, in 2022, it started to be able to write code and do math. And then ChatGPT was released, and with the advent of GPT-4, it started to become really useful for astronomers. At this time, I made Chat Gaia, which is an app that you can use right now on ChatGPT if you have a subscription. And I fed it all the information it needs to know to query the Gaia database. And so you can ask it for a plot of the Pleiades and describe how you want the plot to look, and it'll go out, grab the data, and then use the data and write the code and make a plot just like this. And so now you can see that the capabilities are there to start becoming really useful. And if these capabilities keep going, which it seems that they keep getting better, how is it going to impact astronomy? And so the current benchmarks to track our progress, like I said, are these multiple choice questions. This is Google proof question and answer. It's a very popular one. And this is a direct question right out of that benchmark. You see that this benchmark, it actually covers like many different scientific disciplines, all with multiple choice questions like this one. And you can see it's pretty difficult. Don't ask me to answer it because my STARS course is next semester, but it's pretty difficult, as you can see. And this is the score that these models get based on their release date, compared to the performance of a domain expert scientist. So this is approximately how a physicist would perform on this test if they were only answering the physics questions. And so you can see it's pretty impressive that we're approaching it. And when I made this plot, I was thinking that by the end of the year, it would be superhuman, but really it was about 2 weeks ago that these models became superhuman with the release of O1 from OpenAI. And especially in the physics version of this test, you can see there was a massive jump in performance. And we're clearly going to need harder benchmarks because it's pretty much perfected every single question on this benchmark, which is really crazy. And so we have to think about harder tests for these models, especially in physics. And so once again, like, it seems to have got a great factual knowledge for astronomy, but how do we test its ability to do scientific coding? How do we test its ability to have a physical understanding of the system it's working with, to do data analysis and then analytical reasoning for deriving equations? These are the skills we want to test. And we can kind of think back on history as an inspiration, where we had, a pivotal moment in modern science was when Newton discovered the law of gravity. And he used it based on Brahe's observations of planetary motion. And so we can kind of look back at this as inspiration. And so we decided to base our benchmark around gravitational systems, specifically like binary star systems, because we can simulate them very easily. They're simple systems, and you can ask a lot of interesting questions about them. So this is the benchmark. We have 12 different binary star systems that we simulated. We have the positions of the stars over time, like the X and Y positions, like this plot here. And then from these, only the positions over time of these stars, you can ask questions like, what is the semi-major axis of the system? What is the orbital period? What is the mass of star 1? Or you could think about like more difficult questions where you can modify the gravity of the system and then ask, how did we modify gravity? And so this should be really difficult for the AI to do. And so what we do is we provide this X and Y positions of the stars over time as a pandas data frame to the AI agent, and we let it work with Python. So it can write Python code as much as it wants to work with this data frame to try and answer the question. And it can run into errors and try to fix its errors. It can see its outputs, and it could be like a multi-step process. And then when it's confident in its answer, then it can submit it for grading. And so we can look a little at the simulations, and then we'll see it in action. So some of the simulations have different units to make it a bit more difficult. Some of them are just, we modified the physics a bit, so we modified gravity, or we added drag as like a difficult situation. But most of the simulations, they are just have normal gravity, and they have different mass ratios. We try to vary the ellipticities, off-center it. And so these 12 simulations, we can ask plenty of questions about each of them. So here's it in action. So in this case, I'm asking for the period of the system. And you can see that it can print the data frame. It can realize the data it's working with. It can write code to try and find the period. And then when it's confident, it can submit an answer. And it does this for a bunch of different simulations, because you can ask multiple questions about each one. And each run is independent from the other, so it can't see how it performed in the previous question. So let's look a bit at how it does on the individual questions. So here I ask it to determine the eccentricity. And GPT-4o mini is a smaller model. And you can see that it has, a kind of right idea. It's going to calculate eccentricity with this formula. But when it goes to calculate the semi-major axis and semi-minor axis, it uses a wrong formula. It just uses the maximum of the separation divided by 2, which is not applicable here. So it gets the wrong answer. GPT-4o does something a bit more complex. It assumes the masses of the stars, which is not really good. I didn't tell it the masses, I only gave it the positions over time. So it decides to assume the masses and then try and calculate the specific energy and angular momentum and calculate the eccentricity that way. And it arrives at an answer of 24 bajillion. Which is really crazy, and it doesn't double check its answer. Even though it has the opportunity to double check, it just submits it as is, and it's really confident, which is not really good. But Claude Sonnet, on the other hand, is a good model for Anthropic, and it provides it finds a eccentricity vector, and then this ends up being the correct method, and it gets the right eccentricity. But let's move on to a harder question. This is the one where we modified gravity to be 1 over r to the 2.2 rather than 1 over r squared. And we tell it that we modified gravity, and we told it that we changed the exponent, and we ask it to find the exponent. In the 4o case, it has a good method. It calculates the accelerations and the separations of the stars, and then it tries to fit this gravity law, this 1 over r to the exponent, but something goes wrong in the fit and it gets the wrong answer. Claude Sonnet, on the other hand, takes a few steps to reason, and it actually decides to fit the logarithm of the acceleration and the logarithm of the separation between the stars. And it finds that the slope of this straight line would be the exponent of gravity, which is actually true, and it ends up getting the right answer, which is really impressive. And, maybe Claude knows that it's easier to fit a straight line than to fit this 1 over r like power law. And I won't show you all the results, but I'll summarize in that Claude, out of 179 simulation task pairs, gets 40% correct, which is really good. There's obviously room to improve, but now that we have the benchmark, we can see what's going on and try to see what it needs to work on. And before getting into that, I should say it does this in 47 minutes, which is really, much faster than a human would do. If you were to task a student with 179 questions, probably take a week, and they would probably want more than $3 to do so. So you can already see like the benefits of cheap and fast intelligence that could really speed up science. So where does it go wrong? Well, when we looked at all the incorrect answers, we noticed in plenty of solutions, you have to assume the masses, you have to calculate the masses of the stars. But what we found is that these models would either assume that the masses of stars were 1 kilogram, the mass of the sun, or they would assume that they were just equal masses when calculating the center of mass. And these are wrong assumptions to make, and it showed up in as much as 60% of wrong answers, one of these 3 lines. But this is a simple problem. We might be able to just tell it not to do this. Now that we have the benchmark, we can see that this is where it's going wrong and try to improve it. Other common mistakes is assuming that the orbits were circular and not verifying answers like I was talking about before. And so, if we think into the future and think, okay, now that we have this test, what does it need to work on? Well, obviously it needs to avoid making these rash assumptions, which we can just try and tell it not to. That's like a better prompting, or potentially giving it examples of solving problems different than the problem it's currently working on. That's the few shot. That might improve it. Otherwise, we could have like a team of agents. So you might have one agent that verifies the answer or tries to verify it, and then, asks itself, does this answer make sense? And if not, needs to keep working on it. And in the long term, we need these AI models to have better reasoning and better planning, especially if we want an actual like AI astronomy assistant that needs to do multiple steps over a long time. luckily, these companies are spending hundreds of billions of dollars working on these problems. And we saw the benefits of that recently with the O1 and O1 Mini, which I really want to test on this benchmark as soon as it supports function calling. But these models have the better reasoning and the better planning. And so we should see, as smarter and smarter models come out, they should get better and better at this benchmark. And we're going to need, this is just for version 1, we're going to need much harder benchmarks in the future to track our progress towards this future where we might have these AI research assistants as they get better and better at astronomy. So that's all I have. Thanks.
Thank you very much, Nolan. Yeah, again, very, very impressive. Let's see if we have questions from people online or people on the. In the meantime, I saw that Miguel was answering some of the questions that was on the chat. Thank you very much for that. Is there any question from the attendees? I don't see hands raised. Yeah, I have. While I was looking at this, Nolan, yesterday, I don't know if you had time the chance to see the talk of yesterday. There was, but basically the question is, how do we? So you showed, I mean, you're testing, right? These infrastructures, but how? I mean, to me, towards an AI in astronomers, it looks scary, honestly, in a sense. I mean, do we? Because it's just a matter. So the fact that the machine will, my perception is the fact that the machine will become better is a matter of time, as you made very clear, right? But the problem that it came out yesterday when I was listening to computer scientists that we have lost somehow control over the. So we train the machine, then we get outputs, and the problem now that we have is to understand biases in the outputs, to understand the quality of the output, which is a bit what you're doing. But so exactly, which is a bit what there is a question now on the chat. How do we trust? Is again we go again in the problem of trust. How do we trust the result produced by an AI astronomer? So
yeah.
It's just a matter of time. Then at some point everything will be fine, or because you said, I mean, we need to maintain critical approach, but this requires maybe self-regulation that is difficult to keep.
Totally. So yeah, so working like before language models, and when we were looking at like AI and astronomy projects, we were really thinking about feeding the data into neural networks and then having it, output like H0 or some parameters about the universe. And then that was also another question, like how do we trust what this model's doing? We can't really investigate the internals too much and get a good understanding. In this case with language models, I think it's much easier to verify what they're doing because they're actually doing science the exact same way we are, where they're writing code and working through methods. And if they do a math derivation, they show the steps. And so you can actually look over that and verify. So I think that is, this is actually a really great approach to have it write code. And then obviously, like, if it gets good enough that it starts, writing its own reports, like I said, and writing entire like GitHub repos, then our peer review system is going to have to get, really, really strong if it's reviewing AI content because, yeah, they have these hallucinations. And so when you get this plot at the end that it makes after it analyzed the data set, you're going to definitely have to look through the code and make sure it did everything right, which is usually a lot easier of a task than writing the code in the first place. And so I think in this way, it's definitely going to speed up our workflow.
But
nice.
the bug in the code, it's not that obvious to me that it's easier, but I understand the point. Yeah, it's
sure.
Yes. There is in fact another point. Then we can move on. But again, we will have we can chat further for sure,
sure.
Later in the discussion session. But there is, I will ask you here to give a short answer if you can, because it's infinite. Basically, you can go on forever, I guess. So will the LLM models able, LLM system to predict discover new science?
Yeah, that would require really, really, really intelligent systems. I think right now, I mean, they're obviously really good at interpolating within the domain that they trained on. So if you wanted to go ahead and recreate a paper and re-implement like a paper's methodology, I could see that very easily being done on the horizon by these types of models because they've been trained on the scientific corpora. But to actually go outside this domain and discover new things with developing entirely new methodology, I think that is something that will definitely need to be researched. And if someone can show that's possible, that would be really incredible. But I think that would be extremely difficult.
Yeah. Thank you very much again, Nolan, for the great talk. Let's move to the last talk of this first half. Paula.
I don't have permission to.
You're right. Sorry about that. This is my fault. Here you are. Now you should be able to share the screen.
Okay.
Yes.
Can you see the presentation now?
Yes, perfectly.
Okay, can I start?
Thank you. Please, go ahead.
Okay, so hello everyone. I'm Paula Sanchez Saez. I'm a user support astronomer at ESO. And today we'll tell you the experiments we're doing at the user support department to support users using language models. So first of all, what is the user support department? If you are not an ESO user, maybe you're not familiar with the USD. Basically, at USD, we are the main interface between La Silla Paranal and Observatory and users of the different instruments we have at ESO. Mainly, we are in charge of supporting phase 2, but we also support phase 1. And here you can see, I guess you can see my cursor. Here you see the data flow that we have at ESO. So basically, we have phase 1, where people submit proposals, then phase 2, where people with accepted proposals in service mode submit their materials, and user support astronomers check them. And then in phase 3, the data is available in the archive. So in general, we support phase 2, but we are also involved in the different aspects of the data flow. And also we support post-observations and days operations. So why are we talking about support of users using language models? So basically, we want to solve 2 problems. First of all, sometimes it's quite hard to find information about the different ESO instruments because there are so many and they're complex with different properties, different capabilities. So reading very long manuals can be kind of hard for some users. So the idea is to help them using language models. And also the idea is to help users to find important information that sometimes is hidden in the many websites we have available. At the moment, there is one website that is aimed for this, that is called the Knowledge Base, where it's mostly a frequently asked question website, where you can see different questions and answers, but it's static, and users cannot ask new questions that are not listed there. So a way to solve this is to use ChatGPT or language models in general, and I will skip this a little bit because it has been mentioned a lot, but just to summarize, ChatGPT is this OpenAI service that is based on transformers, and it's a chatbot interface where users can interact in a conversational way. But recently, I think in the last months, it was released a new capability in ChatGPT where you can customize your own ChatGPT using the same kind of techniques that people have been discussing during this workshop. I mean, retrieval augmented generation, or RAG. In particular, in this case, you can provide context and relevant instructions to have a more customized chatbot. And to create this, if you have a paid account, you can create your own GPT very easily using this new GPT tool, where you have to define, well, of course, the name of the GPT, and a description, but the main part is here in blue where you have the instructions and knowledge. And the knowledge is super relevant in this case because you can upload at the moment up to 20 files with a given maximum size. And for us, it's very convenient because we have several manuals that are publicly available, and we can use them as a knowledge base for the GPT that we're creating. So using this technique, we created this ESO manuals tool that is not available openly now. We're still testing this. So what I will show today is not available yet for the users. And we don't know yet if this is the tool that we will release or another tool because we're still experimenting. But the tool basically is supposed to be a virtual version of the support astronomers that we have at USD. And basically it helps you to query information in the different manuals and websites about the different instruments we have available at ESO. And also it's able to address specific questions about this. And as it's using ChatGPT, it's a very inclusive tool because you can use it in different languages, and you can also use the app to interact by voice. So these are the details on how we constructed this. It's super easy to implement once you know the proper instructions and the proper documents. So the tricky part is not creating the tool, but is having the proper text for the instructions. So we uploaded a set of catalogs, all the BLT manuals and a few La Silla manuals. And in the instruction section, we have a very long prompt that I would hope this to be shorter, but unfortunately, after experimenting, I realized that it needs to be very long to be able to provide good answers. Basically, at the beginning, I say, okay, you're a virtual super astronomer, you have to be concise and provide always references for your answers, and then instructions on specific websites to address different questions. So about the different phases of the ESO data flow, and also about how to break some rules, service mode, the ops prep tool, VLTI, etc. And in cases where the tool is not able to find information in these websites, I also included a way to query using Google. So some results. If you compare the answers you get from the classical ChatGPT compared to the ESO manuals GPT, you see clearly the difference. For ChatGPT, it's very hard to answer a simple question as what is an observing block, which is a key component of the ESO ecosystem. While for ESO manuals, it's very easy to answer that question because it's contained in the different manuals and websites. So the user doesn't need to provide any context to get an answer. Also, although they claim that they have the same models available for free users and paid users, you can notice differences in the outputs. For instance, for the question, I need to break an OB rule, when and how to do it. Here in the free version, it asks you to contact directly USD, while in the paid version, it tells you that you have to use the P2 tool to access the waiver request option. So if, of course, you can always request some support from USD, but here is the proper answer. Also, after the experiments, we realized that you need to be very specific in the instruction sections to get proper answers. For instance, about the same question about breaking OB rules, if you don't include any information in the instruction, it's very hard for the tool to realize what is the proper answer. It's again proposing to contact user support directly, while after I included this specific instruction, now it's telling you, okay, you have to use the P2 tool. That is the one that we use for phase 2. So some lessons learned from this experiment is that the classical ChatGPT is not able to answer very simple questions about ESO. So we need a tool like ESO manuals to be able to answer questions without the need of the user providing many information in the prompt. Also, the context section in the tool is super important to be informative. For instance, the name of the documents you upload has to be informative. If you only provide like very cryptic names, it will be super hard for the tool to identify the proper file to find information. That's why when I uploaded the documents to the tool, I had to specify very well in the name the instrument it was referring to in the manual. Also, the model struggles with deprecated instrument modes that are still mentioned in the manuals, for instance, the X-shooter IFU, because as is mentioned several times in the document, for the tool, it's hard to identify that it's a mode that is not longer available. So I had to include in the in the instruction section, a very specific instruction saying, check that the modes are not deprecated. And also, as I mentioned before, the instruction section is too detailed and it could be better, but at the moment with the version that we have available now, the model that is available now with the 04, is we need a very specific instruction section. But a good thing is that changing languages while interacting with the chatbot is very easy. Just you can start a conversation in English and then switch to, for instance, Spanish or German very easily. So it's a very inclusive tool in that sense. Some problems we found, first of all, the limit in the number of documents that you can use for contextual information. At the moment, it's only 20 documents, which is very low for the number of documents that we manage at ESO. Also, as this is a third-party tool, you cannot provide private information. So it's just limited to public documents. And web browsing tends to be a problem for the tool, particularly for some ISO websites, like the knowledge base. It tends to fail because the format of the website is not very friendly for ChatGPT. Of course, as this is a third-party tool, we don't have any control on the quality of the answers provided. And although we always requested in the prompt to provide references, this is not always the case. And when sometimes it provides references, these references are incorrect. And of course, as it's an external tool, it's very hard to have control on future applications. So this was the first experiment we did, but then we started another set of experiments with an in-house solution in order to have more control. So I will tell you about this now. So this in-house test has been done in collaboration with López-Caniego, who is a software developer at ESO. And in particular, we are testing models that are open source. So in particular, we are testing with Mistral AI and Llama. And as this is an in-house test, we can provide private information because this is not publicly available. It's just locally computed. Also, as we know very well the format of the ISO websites, we're using tools to do web scraping that are appropriate for the format of the ISO websites. And as this is a local tool, we have more control on the answers provided. And in particular, we are including checks for hallucinations and the quality of the answers. So this is more or less the flow that we're using now. Of course, this is a preliminary version that can change in the future. So first, we have the question, that is the prompt. And then from this, we use this RAG approach. So we retrieve documents. And in a second step, we grade the documents and check if these documents are relevant for the particular question. If they are not relevant, we transform the query and start the process again. In case the documents are relevant, we generate an answer and then check if the answer is based on the documents by comparing if the answer is more or less contained in the documents. If not, we repeat the process again. And then once the answer generator is approved, we check if the answer is actually answering the question using another LLM. And then if it's answering the question, we provide the output. And if not, we repeat the process again. So it's an iterative process that takes a few seconds. And here you can see an example of the kind of answers we are obtaining now. For instance, how do I submit an ISO proposal? Here you see the answer is very straightforward and provides proper links. If I make the same question to ESO manuals, our own GPT in ChatGPT, you get a very verbose and long answer with several steps. And if you compare with this answer, this one is much better because users don't want to be bombarded by pieces like very long blocks of text. Also, for instance, when the question is not properly written, we have this option to rewrite the question, and that allows you to get answers even though the question maybe is not very well written, like, please tell me about the service modes, OB rules, and advices. It's kind of ambiguous, but it's able to identify properly what is the question about, and it provides always relevant links. As we have control, we have been checking that the links and sections are correct. While if we do the same with the ESO manuals tool, we get again a very long answer with different steps that are maybe not super relevant for the user and without any references. So some lessons we learned with this in-house experiment is that we have more control if we have our own tool, and we can control also the number of documents that are provided to the model. As we are doing this locally and we understand the ESO websites, we can use the proper web scraping tools and not just standard tools like the ones available in ChatGPT. And the quality of the answers are in general more concise and accurate because we have control on the temperature of the model. So at the moment we are using 0 temperature to avoid any hallucination. Of course, it's always possible, but if you use very low temperatures, you can control that. And normally we get proper references. Like in all the tests that I did, the references that were provided were correct. And the reference to ESO manual sections were also correct, while it's not the case for the GPT ESO manuals. So in the future, we are planning to test other open source models like AstroLama that is trained on astronomical context, like using papers from the archive. Also have conversation history, because at the moment, this is possible with ChatGPT, but we are not using this in our in-house approach because that will need some modifications. So it's part of the future work. And of course, we will need to develop a chat interface because at the moment, we only have the script that is running, but we don't have an interface where users can connect. And that's it. So let me know if you have any questions.
Thank you very much, Paula, for the talk and again, the interesting exercises. We have time for one question, actually, so and then we can move to the coffee break. I don't know if there are questions from the people in the chat or from people in Zoom, but in case I have my question, indeed, I have a curiosity, Paula. It's because we were talking about control, I mean, quality control, basically. And you say we have got very good quality control, but I was trying to picture this in operation, right? So imagine this goes out, and then community, for example, during close to the deadline submission of a proposal, for example, we might imagine that there are 100 people using this tool to get suggestion inputs to navigate and get how do I get this to understand. But how do we control these answers and maybe to feedback our I don't know, for example, how do we spot that there is a problem in our user manual, for example, so we can feedback some feedback, I guess, on the source.
Yeah, at the moment this is done in these steps. So we're relying on the we are also using an LLM to grade the quality of the answer. Maybe this can be done in a more astronomical way, like having a person checking, like in a first, in a testing phase, if the answers are correct. But actually, that's the experiment I'm doing now. But if we want to do this like very automatically and for several users at the same time, we will have to rely on the tools. So a way to do this is comparing text that is generated with what is contained in the documents. That's why we have this part here that is checking if the text that is in the generated answer is similar to what is in the documents. That's a possible way to do this automatically. But yeah, unfortunately, having a perfect way to check this with the tools that we have at the moment is very, very hard.
Yeah.
But that's why we're doing this experiment with some ESO students and staff to see if they found problems. And that's why we haven't released this yet to the community.
Of course, because it's an interesting concept, the similar. Because similar, whether an answer is similar to what is, so because the similarity found by the LLM model, I guess, is the matter of statistics. So it's a language, right? So it put in words, it's not a conceptual, right? Similarity. So
yeah, so you expect that in the embedding you will have some knowledge in the vector, like it's not just like words. It's supposed to be able to relate the content of the words, but of course it's not perfect. So yeah, this is something we need to investigate.
Okay, good. Thank you very much, Paula, and thank you to all the speakers on the first half of this event. So now we move to the coffee break. We will shorten the coffee break. Unfortunately, we will start again at 4 o'clock local time, of course. I will share that now. And so see you. I will leave the Zoom on. So please be aware that if you will be talking, you will be seen on YouTube. And people on YouTube, we are back in 10 minutes, 15 minutes. See you. Thank you very much. Okay, thank you very much, everyone, again for being with us. We are back. Funny because I put a slide. There was a typo in my slide, so you clearly see it wasn't done by a GPT. It was done by me. I made a typo in my slide. So we now reconvene. It's 6 o'clock. We can go back to our program. And the first, we have a contributed talk, again, given by two speakers, in this case, Christopher Stubbs and Merlin Fisher-Levine. And I hope I pronounced it correctly. I apologize if I made mistakes. And thank you very much for being with us. And after that, we have an invited talk, and then we continue with a discussion. So I will say, Christophe and Merlin, you can start. Oh, wait a second. I need to make you a co-chair. Sorry, that's always my co-host. Sorry. Okay, now you are. Merlin, I made you, and now Christopher, you are also co-host, so you can both share your screen. Okay. Yes.
Okay. How's that?
Perfect. There we see your screen.
Yep. 1 second.
Please.
Is that better?
Perfect.
Okay. So, hi, everybody. First of all, thanks to everyone for a really interesting set of talks and discussions so far. I'm Christopher Stubbs. I work at Harvard University, and I'm reporting on behalf of the colleagues who are listed here some of the things we've been doing to play with generative AI, a little bit on the other end of the astronomical process, more directed towards commissioning and operation of telescopes. But I think you'll see a lot of the themes that have come up will be recurrent in this talk. So we're working on the Rubin Observatory, which is a project previously known as LSST. It's an 8.4 meter wide field of view system, 3.2 gigapixels, with a plan to survey the entire sky in 6 bands over 10 years. And you can see the telescope in the top right picture, the camera in the bottom right, and the pass bands that essentially go from the UV cutoff of the atmosphere to the band gap of silicon in broad pass bands. So this project is transitioning from construction to commissioning. The commissioning camera and the secondary mirror are both in place. The primary and tertiary mirror will be installed in the coming weeks. In the commissioning and operation of the system, there's a large amount of information that flows into an engineering database. Everything from the telescope control system, the camera control system, an environmental monitoring system, image characteristics that are extracted from images in real time, such as the seeing, transparency, and things like that, processing, networking, data pipeline status. And in addition, we have a smaller telescope that is dedicated to measuring the optical transmission of the atmosphere using spectrophotometry. And that telescope has been in operation for the last 2 years. And we'll show you examples today that draw on that data to operate generative AI. So it's a big, expensive project. It's around a $600 million project. And so it necessarily has a big and complicated project management structure, including software management that was established decades ago. So the work breakdown structure of the software does not very easily accommodate a disruptive technology coming in from nowhere like generative artificial intelligence. All the programmers already have a full-time job. And if you go to the project managers and say, hey, this whole GPT thing is really cool, why don't you give us 2 or 3 programmers so we can fold this into what we're doing? The answer that you get is basically no, thank you. We have deliverables and we have a plan and everything's budgeted. So we, on this talk, have been exploring the use of natural language analytics with large language models to look at ways to increase the efficiency of the commissioning of the telescope. But I do want to emphasize that this is a research project and not currently part of the mainstream project endeavor. So what are the different ways that you can use these generative AI tools? And we've heard a number of these examples so far in this conference. One possibility is to use things like coding assistants where you run a Jupyter notebook locally at the data facility that has access to the data, and you basically use ChatGPT to generate Python code. You cut and paste it from their browser interface into your notebook, and you run it in the notebook, and if it generates errors, you paste the errors and you give it back to GPT and say, oh no, go fix this, and you iterate using it as a programming assistant. That's basically standard GPT-assisted code development. Another example, which we heard about in the talk from ESO a moment ago, is to basically send your data or send information to OpenAI or some other LLM model and have it internally run some process, either in data analytics or with RAG encoded documents. And you can do that either through its browser or by making a custom ChatGPT. The third option is to use API calls to large language models from within a Jupyter notebook, and that's what we're going to spend most of our time on here today. So we've implemented something that we call AstroChat, which is an acronym that GPT made for itself, and you can see the decoding of the acronym on the bottom, so we don't take credit for the acronym. Just to compare these really quick, the columns include the different methods on the left-hand side. Where the computations happen is the second column. Where the data reside is the third column. The extent to which you capture context for the discussion is the fourth column. And the fifth column shows what capabilities of the large language models you're actually using. So if you use it to do code generation, the code runs locally, the data are local, the context is stored on the LLM side, and it uses code generation and debugging with a natural language interface. If you use some of the built-in analytics or make a custom GPT, the computations run on the OpenAI side. The data is limited to what you transfer to them. It does retain the context of the history of the conversations, and you get to exploit the full capabilities of natural language interpretation and analytics and visualization. The third row on the bottom is the one we'll discuss in some detail today, and that's to make API calls from within notebook cells to GPT models on the outside. In that case, the computation runs locally on your system, which is the same place where the large data set resides. So in some ways, that's the advantage to doing it this way. In the way that we've implemented it, it doesn't currently store persistent context on the OpenAI end, but there are ways to do that. One of the advantages of doing it this way is you get access to parameters that are not fully exposed otherwise. So you can explicitly set the temperature, and you can exploit code generation, natural language interaction, and tool use. So this is a flow chart of what we've implemented. On the left-hand side is the user who asks a natural language question typed into a Jupyter notebook. That gets interpreted by LangChain and sends a structured prompt with an API call to an OpenAI agent or tool. And we also point the tool at the local data repository that's stored on our machine. That then sends the prompt in the query over to OpenAI. We get the answer back, and then through LangChain, we strip out the executable Python code that it sends back, and that Python code then runs automatically on the local machine. So here's an example just drawn from one of the cells in the notebook to show you how easy it is to implement this. Day obs is a date stamp that points it to a particular single night of observation on the auxiliary telescope. We insert the API key locally, and then we invoke this chat object by passing it the pointer to the data, set a few parameters, give it a model name, tell it in what way it should respond, and then from that point on, essentially, we can do queries. So here's an example. In the top line, you can see a natural language prompt that says, can you make a histogram of full width half max of images that have non-NaN full width half max information? And boom, up comes the histogram drawing on the data that is local to where this code is running. Back the Python code that it generates so that you can validate that. And if you like, copy and paste and modify the code into a cell in the notebook. So we're essentially using it as a natural language triggered code generator, and the code runs automatically locally. Furthermore, intermediate data products like data frames that are constructed on the fly are persistent in the notebook and actually reside there. And oh, here we go. So just to show you an example of, here's the header for that intermediate data product that was generated. Here's another example. Please make a pie chart that indicates how many images of each type were taken. So we have darks, biases, flats, wavefront sensing, engineering tests, acquisition, and science images. We can say, please assess the extent to which image motion degradation depends on declination, and please give me a plot. We know we have tracking problems with the telescope near the south celestial pole where the tracking rate is low. And this, in fact, illustrates that fact for us. So another thing that we like to track is over what air mass range did we observe different objects. So what we're trying to convey to you here is it's a lot more efficient to pose these natural language questions and have it generate the code that then generates the answers for us than it would be to write notebook cells on our own on the fly. So what are the pluses and minuses of these different ways of doing business? In the top row, if you use ChatGPT generated Python code and just paste it into your notebook, it's pretty straightforward. The data code generation tool, I think, requires an OpenAI account. You get natural language requests, but you really don't get back necessarily the results of analysis because everything is stored on the, I'm stumbling around here. We get natural language requests for code blocks, and you can actually ask for natural language processing of other things, but it can't interact with the data directly because the data are sitting on our side. If you upload things and run their data analytics tool, you can pose analytical questions in natural language and generate plots and the like, but it requires an OpenAI account. There's a limited amount of data that can be transferred, as was made in the ESO talk. The potential data privacy and confidentiality issues are a problem. When we tried to upload HDF data structures, it failed and we had to convert them to CSV files. And it's a bit clumsy to have this code and overrunning on their side, and you can't get to the intermediate data products. The bottom line is what we've shown you here today, which is to make API calls from within notebook cells. It lets you execute natural language queries and have it automatically run Python code within the notebook. The computation is local on our side, and all it requires is an API key. Not every user has to have an OpenAI account. On the other hand, it requires some software engineering to parse out the executable code that comes back from OpenAI. We've had some challenges keeping up with evolution in the versions of LangChain. Things that worked one day don't work the next day. And we need to keep maintaining the software. And at the moment, the context is not stored on the OpenAI side, although that is something that we can do. So here are my sort of caveats and disclaimers. This is not a mainstream Rubin project effort. It's more of an insurrectionist attempt at R&D. Any opinions here expressed are ours as individuals and not that of the Rubin project. It's a little bit scary in a way to have a GPT agent automatically generate code that executes on the fly on our end. And you could imagine that might have adverse consequences. But I think when we compare these OpenAI issues, I think we need to be realistic about what we're comparing it against. So we already have inexperienced students and, oh my God, faculty that are floundering around in our notebooks doing all kinds of bad things, and it's not clear that this is going to be any worse. And then finally, the standard generative AI caveats about hallucinations, lack of repeatability, and error checking clearly apply. So where do we see this going in the future? We will be experimenting with this during Rubin's commissioning phase to try to tighten up the diagnosis, evaluation, and rectification loop of engineering. We're working to expand the data access on our side to include all our streamed engineering data, which will essentially boil down to OpenAI formulated SQL queries. Another work in progress is to vector encode all of our documentation from Confluence, from DocuShare, from Jira, and provide natural language browsing to that large volume of documentation. And in parallel with the talk that we heard from ESA, we do expect LLM-based science analysis accessing the catalog of data from the Rubin project. Thanks for your attention.
Thank you very much, Christopher. Merlin was very active on the chat, just clarifying a few points. So Merlin, you're not giving another talk, basically. You're sharing the ownership, basically, of the talk, in a sense.
Yeah, exactly.
Like
so, I mean, I guess the things that I would just add, particularly because the people on YouTube won't have access to the chat, is just to emphasize that the reason for running the code locally is that when we say large data, the engineering facilities database is currently, you know, order of 100 terabytes and will be growing to a petabyte by year 10 of high frequency time series data that you want to be able to correlate things that you see in your image data with and do time-based queries of, and that the imaging and catalog data will be growing to tens up to hundreds of petabytes by year 10. And so anything that involves uploading that is obviously completely intractable, not to mention sort of speed of running queries locally. So that's one reason why you kind of have to do it this way, because the code has to run next to the data. The data cannot be transferred. And I think the other thing to emphasize is the kind of one of the selling points here is that because after each execution of a cell, all of the agents' sandbox local variables are exported, you're genuinely in collaboration with the agent. So at any point, you can just take the code that it's generated and it will run in your notebook like it did inside the agent sandbox. So you go, oh, okay, I want to like do this and take that variable and multiply this thing by that thing and plot that. You know, if at some point it's more frustrating to work via natural language, you can just take over and code because you and it have access to all of the same data.
Okay. Thanks for the clarification. Let me check. I think there is a question from, so I don't know whether there is a question online, but I'm not sure anymore what time was, to who we was referring. I don't know, I can read it on YouTube. I can read the question. So the question is concerning the trust on LLM models, but probably is related, maybe something that we can capture during the discussion. Something I wanted to ask is, unless there are more questions, is specifically related to, in fact, the commissioning a telescope, or let's say operation on the telescope. Of course, is something I working at is something that I find very fascinating. So the aspect of, so basically what you described, just to see how you envisioned it, beyond the commission, but also in general. So we do daily quality control at the telescope, right? We control, I don't know, we are monitoring temperatures, we are monitoring, so instrumental properties, like instruments, telescope properties, but also data quality. So you monitor, as for example, the PSF that Christopher showed. So you monitor the PSF, the full width and maximum, or the signal to noise, or whatever. So, but my question is, so we do this already, and I think kind of efficiently in a sense. So we have monitors that, so we set up, okay, it takes maybe a bit of time at the beginning to set up the proper KPI, let's call it like that. Okay, I don't know if this KPI is the right word, but then you can monitor the health status of your instrument and your telescope. So do you foresee that the use of LLM models or GPT-like model will be more beneficial because it will give you more analytic power in the future to understand what's happening with the telescope or with the data? And the second question I have is if you can use also this technology in operation itself with the telescope, I don't know, focus the mirror, for example, or guiding the telescope, or I don't know, you see.
Yeah. So let me give you an example. You know, we've all been at telescopes, I think, where you have this wall of monitors that present a lot of graphs, right? Somebody thought we're going to present information that people might find useful. Here's an example. Imagine you plot wind speed versus time, and most telescopes have a wind speed closure limit. So if you're the telescope and you want to ask, wind is getting stronger and stronger and stronger, I wonder when it's going to cross the wind limit. Currently, you go click, 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 click through a bunch of screens till you find wind speed versus time. And then with your eye, you kind of draw a line and you say, well, you know, I think it's trending like this and maybe it'll happen at 3 a.m. It really changes the way you think about this. If you were to ask an LLM, look at the wind speed data, not just from tonight, but from similar environmental conditions, and please make a prediction with confidence intervals of when you think the telescope is going to hit the wind limit, right? It changes the way you think about running these systems, I think, in a very profound way. So I do think in the long run, we will end up there, personally.
So it's forecasting, basically, power of forecasting.
And just monitoring.
Yeah.
I think, you know, a lot of the things that we rely on telescope operators to do would be augmented by these tools, I think, in the long run.
Okay, thanks. I don't know, Merlin, you want to add something? Or...
Yeah, I mean, one thing is you always have more plots that you might make that you don't want to add because at some point you're not necessarily adding to the signal for the most part, but there'll be times when there are plots that you would like that you don't want displayed by default. You know, things that you think, oh, I wonder if that correlates with this. And then rather than having to go to a notebook and write everything from scratch, you can just kind of write it out in English and have it come back as a plot, and you can see exactly how it's been done. The other thing is that, like, this engineering facilities database has, I don't know, 2,000 or 3,000 topics in its schema, and it's all defined in XML. And so making a kind of RAG type tool that reads the XML, looks at what the description of every single topic in the schema for this giant database is, can then use its own intelligence to kind of say, oh, I'm going to make this query and that query and correlate that against this. Because you can say, oh, can you see anything that might correlate with this? And then using retrieval augmented generation, it then knows which topics, which you might even not have an awareness of because there's 3,000 different bits of time series data. So it will be able to do things that you don't even think to do, and also generate the plots and retrieve the data automatically where you may not remember how to instantiate the client to get the data out of the database, let alone how to quickly plot it against this thing and that thing. So I think it really opens up a whole new world of things that you can do almost trivially that currently are so difficult or beyond things that you'd imagine, that it will hopefully really change how we look at stuff.
Okay, fantastic. Thank you very much. So thank you both again for the talk, and then now we go to the last talk of today. Is an invited talk by Yuan-Sen TING. Hi, Yuan-Sen.
Hi, I just realized I couldn't share the screen. Like,
yes, you're right. It's always my fault. When this happens, it's my fault. So don't worry.
No.
Now you are able.
Let me try to share now.
Yeah, please go ahead.
Can you see my screen?
Very well. Yes.
Okay. And should I get started?
Yes, please go ahead.
Okay. Good morning, everybody. It's really quite funny that because Chris was my first advisor at Harvard, and we were working on completely different things. But now we are both working on AI astronomer. So my name is Yuan-Sen. I am a associate professor at OSU, and the work that I will be presenting today is really, I'm just representing quite a lot other work from quite a lot of people. But the goal today is to continue the discussion from what we have heard from Chris and also like Nolan on how we can do AI astronomer, right? So let me start by saying that we are all here. Of course, there are lots of excitement in AI for science. In fact, the 2 AI center in astronomy just get announced. And with so much money, of course, the question that we often get asked is whether or not this AI for astronomy is a hype, a myth, or a real deal, right? The proponent of AI for science, of course, will point to the shining example of the AlphaFold, right? So if you think about life sciences now, is completely unimaginable 5 to 10 years ago. So if you work on a PhD in life sciences, the chances that the project that you're working on now is quite different from the PhD from 5 years ago. The question that people like often ask, of course, is like what it will be sort of the AlphaFold moment in astronomy, right? So we know there are lots of interest, and of course there are lots of people have been like, including myself, has been working on the application of AI in astronomy. So lots of things that we have been doing in the last 10 years or last decade, mostly like focusing on, for example, like advancing the statistic with AI. So what we call now the SVI, the simulation-based inferences. And of course, there are lots of work that has also been dedicated to, say, the Rubin Observatory to do the classifier and broker and emulation of expensive simulation. But one common thread here is that most of the effort in AI for astronomy, of course, are still like focusing on individual downstream tasks. That itself is, of course, quite important, but of course, like that itself will not rise to the level of AlphaFold. Why that is the case? Because astronomy is not biology. So the complexity that we are dealing with in astronomy is much lower than biology. So like if you think about a single task, quite often what we have is we have some data, we have some theory, we analyze the data and decide if the theory is true or false. And in the case of biology, optimizing individual downstream tasks can be important because the complexity is high, and quite often they are bottlenecked by individual tasks. So think about protein folding is a single task, but it's a very important task. And this is why the AlphaFold has made a big impact. Because the complexity of astronomy is much lower, we have already a very successful models and pipeline, right? So there are not many questions in astronomy in terms of individual tasks. We cannot do well with, I don't know, like linear regression or Gaussian process. Of course, like you can use deep learning to improve on that, but the improvement will be most likely like 5 to 10%. So what could be perhaps a better use of AI in astronomy? I think like many speakers in this session has touched upon that, which is the idea of AI like astronomer, right? And a lot of people is also talk about in the near future and maybe in the long run, AI astronomer will be here. My goal like today is to convince you that it's already here. So we have a lot of talk in AI to talk about human in the loop, but perhaps it's more important to talk about how to make human out the loop, right? So in order to have an AI like astronomer, it's important to ask what role the human has in terms of the research. So even though we are not bottlenecked by individual tasks, quite often it is still the human who make the plan, right? So you break down the question to individual tasks, and then the AI can take over. So a lot of the things like what Chris has mentioned and what like Nolan has mentioned, we are still copy and pasting and correcting the codes from the human perspective and know what is right and wrong. But the question perhaps we should ask is this type of reasoning and planning cannot be learned. And it turns out that you can actually let LLM to learn how to break down a question and make plan by open world exploration. This is also the paper that we just put on archive yesterday. Actually, the first author, Zhe Chang, will be talking about this tomorrow. So here I will give you a very quick overview. I will highly encourage you to come to his talk because I think it's really a very exciting line of research. So what is the idea here? So the idea is actually very similar to O1. So if you look at the differences between O1 and GPT-4o, the key differences here is really the idea of self-play reinforcement learning. So what's the idea here? In the very classical way of thinking about machine learning, you have the annotated data, and then you do a mapping between X to Y. So that's a very simple task. But we have also learned over time that we can go beyond the annotated data. We can use unlabeled data. This is the the fundamentals of all the large language models, but also the other effort on foundational models. So you can just ask it to do some pre-text tasks, and it will learn pretty well. But that itself, of course, still have a lot of limitation, because ultimately we have exhausted all the data on the internet. So what is the next ring here? So people have been talking a lot of interacting with the physical world. So even you might not have the data, as long as you have a task, and just like the alpha 0, you can improve by self-play. So you are making plan all the time, but you hope that you can triage the plan that actually works. And that's also the idea that we try to tackle here. We are looking at a question that is slightly different from Chris and also Nolan. So we are looking at the fitting of the SED of a galaxy, say from James Webb. And this task turned out to be quite complex, right? So you think about how a human will tackle the fitting of an SED. Like your first year grad student, you give him the James Webb the data, he or she feed the data and find some discrepancy. And then he or she will run to you and say, hey, this fitting failed. As a human, what you would do is reflect on the patterns, right? So you will say, maybe what you should do is to change the models. So you will do a lot of variation of the models, including changing the dust and changing the star formation history. But all this action is extremely vast. In principle, it's just a optimization problems, but you would not do that, right? Because the action space is extremely vast, and you're quite often using the human to make the plan, to break down the question, and use your experience to navigate the landscape. And this is also what we try to mimic here. So we call that Mephisto, because Mephisto is a demon that trade the soul with knowledge, which is what we are doing here. So in short, the Mephisto is a collaboration of different agents, and each agent is doing a different task. Of course, this is much simpler to say than to be done, because each of these agents, of course, is very extremely fine-tuned in terms of fine-tuning or prompting or RAG to carry out the individual task. But the broad idea here is that you have some SED fitting, you fail, and you try to do tree search. So in Alpha 0 is a Monte Carlo tree search, but in LLM, there are lots of exploration on the tree of thoughts. So you are exploring all the possible options. You have an agent that will propose the actions. You have the agents that will execute the code. So we have seen a lot of code assistant here. But more importantly, you have the agents that will evaluate the different actions. So you have propose a tree of thoughts of actions, and you will try to understand why some action works and why some action do not work. And ultimately, you will distill all this knowledge and try to append that back either as a context, or you can append that back as a training. And this is sort of the widely believed how O1 is trained. And in fact, Claude 3.5, you try to bypass the non-printing token. You can also see that Claude 3.5 is doing a lot of this chain of thoughts and tree of thoughts and optimize over that. The point here is that this tree of thoughts can be summarized. So you can keep improving the LLM by self-play. And I will let Zechang to tell you the details and how we have deployed that in real data and find real discovery. But if you look at this plot, it tells you a lot, right? So the dashed line here show you what the GPT-4o could do, which is the native models. So the GPT-4o can do something, we all know that. But this type of multiple agent and self-play reinforcement or learning can really improve the strategy. So as more game you play, you collect more and more knowledge, even though this knowledge is not in the internet. But because the LLM is smart enough, some of the plan do works, and you will remember what works and what do not works. So I will also let Zechang to talk about that more tomorrow. But the point here is that we talk about in long run or in the near future, but no, it's already here, right? So you think about the SED plot, the SED fitting. we now can do end-to-end and analysis of SED with different variation of models at the human level reasoning. In fact, I would argue that some of that is super human. And the key here is not to use the native LLM. It's just doing what OpenAI did for O1. So you do self-play and try to improve on that through a self-play. Why this is important, I think Chris give a very good example, thinking about like LSST and Rubin or Euclid. Most of the sources that we observe, most of them will get like triage right away, right? So I often make the jokes that 99.99% of the SED will never see the light of a grad student a laptop, right? So most of them is not analyzed by human, and we are missing out a lot of unknown. In principle, this type of agentic research can be deployed massively, and you can reason about all the SED and find all the sources that, despite we have navigate over all the action space, the SED with the current physics fail to explain. So do come to Zechang talks tomorrow on the details, but all this come with a catch. The catch here is, well, you need just like grad student costs money, LLM costs money as well, right? So if you look at the reasoning that we need to do in SED, we have fine-tuned that like massively, but it's very similar to what Nolan showed. It costs about $1 or like per source. Like might think, well, like $1 of course is cheaper than a grad student, until you realize that, well, LSST and Euclid have 1 billion sources, and therefore in principle you will cost $1 billion to analyze all the sources, which is about the same as the build cost. So imagine if I go to ESA and say I want to double the budget. That's the case that we are in. So we could really start to have an AI like astronomer for specific tasks through a self-play, but cost is the problem. And this leads to some of what I want to talk about today, which is how do we get there in a cost effective way, which is something that we have been exploring quite a lot in AstroMLab. So who are the AstroMLabs? So the AstroMLab used to be the core teams of the AstroLama and in UTBD, but then we branch off to work with people in the national labs to scale up the training, right? So this consists of people in the ADS, in the national labs, and also some NLP experts. And of course, we have seen a lot of benchmark, right? But even in the QA, in the astronomy QA, there are really not many good science QA. So we have the physics QA, but that is quite different from the astronomy. So we ended up working with the Argonne national labs to curate a bunch of high quality QA, a combination of human prompting, but also with the LLM. So this is the typical example that we can come up with, which is pretty hard, right? So the point here is that most of these are extracted from the annual review of astronomy and astrophysics, and therefore they are asking mostly expert-like questions. So you can think about this as grad student general exam, but generally slightly more involved than that. So with some benchmarking, you can start to look at the models. There are lots of models. So I write this 45 pages of paper in July, which is completely obsolete now. I'm not sure why I do that in July, because there are a lot more models. The point is that even in astronomy, you can see that some of these so-called flagship models can differ by a lot. You can go from 60 to 85%. And more importantly, of course, is the comparison between the score and the cost, right? So here is how much it costs for about 100,000 token, which is what is needed for the analysis of the SED. And there are few things to show here. One is that, of course, cheaper models are not as good. So there is a strong correlation between the cost and the performance. But more importantly, you can see that the performance can vary by a lot, right? So even like the models that thought to be really strong in the other benchmark, like the Gemini 1.5 Pro, is 2 orders of magnitude worse than Claude, meaning that if you're using a Gemini, then you are perhaps like paying 100 times more than you need in terms of a robust Q&A. But more importantly, in the SED like fitting paper, we do find that sort of the reasoning ability of a GPT-4o is non-negotiable. Because in order for reinforcement learning to work, some of your plan has to work, right? So you are reinforcing on things that works. But if all your plan sucks, then you never like improve. So therefore, you do need something like the GPT-4o, which leaves us with very few proprietary models, and all of them are either as expensive or more expensive than the GPT-4o, which is bad luck. So we look for maybe the other options, right? So beyond the proprietary models, one option is looking at the open weights models. So as we all know, in academic setting, it's much easier to get the GPU time than grants. So it might like make sense to trade off the API cost with a GPU. And we also know that the GPU is become quite exciting. The open weight options, just because some of these open weight models are comparable than the proprietary models. But with a catch, because most of these open source models are only as good, only at the 70 billion parameters and beyond. And one digression in the 45 pages that we do is more than just like ranking the models. So we do try to identify what is the limitation for different like question that the different models get wrong, as well as how well it do in the other subfield, like in terms of like subfield. There are lots of the discussion in the paper talk about why some models are worse in some domain than the other, and we conjecture that is because of the training a cutoff. And we also in this conference we talk a lot on the trust worthiness, how well the LLM know when it knows, and how well it does know that it does not know. And this is a surprising plot, because you can see that some of the older model, again, I'm sorry that I shit on the Gemini a lot, because it turns out to be the case that the Gemini is actually not well calibrated. So here showing you the confidence shown by the LLM versus the actual performance. But interestingly, the next generation of models that came out, in the last 4 months, like Claude 3.5 or GPT-4o or Claude, the big Claude, is very well calibrated. In fact, you can argue that most of the LLM is a bit too humble, right? So they always underestimated how good they are, but they actually know when they know, and they will tell you they don't know when you ask. So the upshot here is that open weight models are options, but only at the 70 billion parameters models, right? And that do not solve the problems, because you are only turning one question to the other. So you have a insurmountable amount of cost to a insurmountable amount of GPU cost. I have done the calculation for you. So if you want to run the Llama 3.1 or 70B on 4 H100 GPUs, then it will give you about 100 tokens per second. What this means is that if you want to analyze the billion sources from Euclid or LSST, it will cost you about 1,000 GPUs running for 30 years. So this is of course not an option, which is lead to where we started. So the starting point of AstroLlama, that even back in the time in UTBD, is to ask the question: is it possible, given that we have very specific tasks, can we actually train on lightweight models to perform well on the astronomical tasks? This is of course a very loaded question, depending on the benchmark. But before that, we really do not have any benchmark in astronomy, right? So we release some models, we assume that it works well, but turns out that is not the case. If you look at the current benchmark that we did, you look at the MCQ, the horizontal line show you the native like performance of Llama 2, which is what we trained based on like a year ago. But turns out that like if you train on that, you actually lost about 20 points of performance. And this need not to be the case. We have learned over time that how to improve on that, which is what we have been working on for the last year or so. Most of these models that I mentioned will be released by the end of this week. This new series of AstroLlama. So if you improve on the training data, you spend lots of time to curate your SFT set. You can reach to the point where you are not hurting the models, but you are not improving the models. So for 8 billion and 7 billion parameter, it's really hard to improve on the models. But that do not mean that continual pre-training do not work. Actually, we show that like in terms of the Llama 2 70B, if you go to the 70B models, if you curate your data well, you can start to improve on the performance. And the performance is really quite close to the old version of Claude, and which is quite like impressive. So what have we learned? So we have burned through about 100,000 like GPU hours on national like clusters. So what we have learned here is that benchmarking is the key, right? So a lot of people are very interested in training like less specialized LLM. But like, without the benchmarking, is really like he says, she says. But it's important to have a very objective like benchmarking to ground the models. And we have also learned in a hard way that using the archive data, which is what we started with, even with the continual like pre-training, is not enough to improve the models. So obviously, the very strong models have seen all the archive data, and even like giving higher weight on those, most of the time don't like improve on the models, which make it really hard for academic to improve on the models. And also training on small models, most of the time like do not work. So we have some plan to figure out, we have to figure out some of the tricks that might make this work. But at least like as of now, most of the improvement do come from the 70 billion models with really expensive curation of the astronomy literature. So what should we do, right? So this do not solve the problem, meaning that we are still stuck with the 70 billion models. Warren Buffett said if like there's nothing to do, like do nothing, which is a good advice, because we know that in the open world, like capitalism, yay, there are lots of competition in price, right? So if you look at some of the models are extremely cheap, they are ridiculously cheap, right? So some of these models can read the 100 years of solitude with 3 cents, right? You can read the whole archive with $40. The problem here, of course, is that these cheap models are not as good. So we have shown that if you look at the cheap models, they are just like orders of magnitude worse than the flagship models. But not all hope is lost, because you can look at each time, like even in the cheaper models, they tend to be more and more like affordable like over time. And in fact, in the paper, we also like look at the exponential time scale of improvement, meaning that if I want to reach a certain score, how fast the price is dropping to reach the same Q&A ability in astronomy. And the time scale is 3 to 6 months, which means that like, even though we say cost $1 billion to analyze the Euclid's data, in 3 months or 6 months, like it will be 100 million. In 3 to 6 months, like it will be like 10 million. So then like it will be 1% of the cost. And I think there are lots of excitement. I think the future is already here, like at least for some of the tasks. And this is really important, because I started as a theorist, and I really layman about the state of the research that we are in, because I like the old time when we do not have a lot of data, but the human are forced to think about the theory, right? We know that we need more data, so we collect more data, and hopefully that we become more sophisticated. But like actually we become bogged down by all the survey that we need to run, because we need to keep the thing like running. We need to train the grad student to write the Python code and try to analyze the data. And we end up to be like data rich, but theory poor. So hopefully with sort of the collaboration between AIs and human, we can go back to the good old time where the AI have exhausted all the data and tell you what is the outliers, and the human can do the hard part, right? So I will leave you with this code that I like, and I will take any question that you might have.
Thank you very much, Yuan-Sen. Thank you for really actually perfect in time, and thank you for the great talk. So let's see if we have questions specific to this talk. Well, while we are waiting, I have a question actually myself. So when you compare the performance, so different LLM models, like you show in different plots. So
right.
This is, I was wondering, this is specifically related to the, let's say, the astrophysical physics context? Or
so the benchmarking is specifically on astronomy Q&A. So,
okay.
so it does not mean that you will translate into like astronomy like coding. So we definitely need like something like the gravity bench. In fact, the study that we do in like SCD is also a good like benchmark, because we do try to swap out the other like backbones, and it does not work. So once you go to cheaper models, the whole self-play just fail.
I see. But does it mean that I mean, maybe I'm saying the obvious, but this means that this strongly depends on the training set that was used to train the LLM. What I mean, right?
It's true, but I don't think it's really the training, right? So the point here is that you always have some task that is not in the training. And in fact, most of the the astronomy things that we do, you cannot just improve on the archive, because like no one will say, I tried this and it failed, right? All paper reads like, I am a genius. I know this right away. This is the plan that works. So what is really interesting here is that when you reach to a certain intelligence in AI, you can start to play the games. You can start to just operate like on its own and learn like over time. Like just like a grad student, you let it to play a certain task and ask it to come up with plans and triage the plans and figure out what works and memorize what works. So I think that strategy is much more like fruitful.
Okay, but how do you control the possibility of biases in the question? So the more you interface, the more you know you are biased interface, you ingest biases, basically, in a sense.
Yeah, it's certainly a danger, right? So you can think about, if I feed the SCD and the native like models really like to change the extinction, then you figure that this works, but you miss out the other like options that works. There is like possibility that that have this problem, but as Chris say, you know, the student and faculty do the same thing. You always have some bias on what works and what do not works. So how to really own that in and make sure that you really start to create more diverse plan, which is, I would encourage you to read the paper. It seemingly is a simple idea, but it's actually a very, we spent like a year to figure out like how to encourage the diverse actions, and how to do like breadth first search and depth first search. So all this can be in a way be coded, because you can encourage that to do more breadth first search instead of depth first search. And this is very similar to AlphaZero. So there's no ground truth, but you need to play the games.
Okay, and maybe I have last, since I don't see hands raised, so in fact, I welcome all the speakers, in fact, to come online. I see they are coming online, so please, we move to maybe a bit more discussion. But my question there was a sentence that I was interested in. You said basically the Astro pH basically is not enough, data is not enough, you said.
Just a empirical fact, right? So it also depends on how you curate the data. So the plot that I show is really following the same training routine in the first AstroLlama, where we take the abstract like introduction and conclusion, but we then since to expand it to the full text And then that is quite not clean. So there are options that we try to actually work like better, which is in the paper, we can train on this, the summary. So the information per token is higher, and you can improve like based on that. If you look at the improvement from the old AstroLlama to what we will release, like even in the small models, is just predicated that you can use a lot of algorithmic way to clean up the information in the tokens. So the information per tokens.
Okay. Okay. Thank you again. So now we can move to the general discussion. I welcome everyone to. Sorry, I lost a window where I had the chat. So just because I'm also monitoring the YouTube chat. So there was something posted on a question or a comment posted on the YouTube chat, which I think is for a general discussion. It's still, so I will read what is written, and it's still about trust again. So we go back to that point, right? Trust or LLM. So concerning the trust in the LLM, aren't the hallucination, and that's an important aspect, hallucination partly caused by hand tuning or politically correctness, not to say I do not know, so exactly, or bad control of input that training data. And in fact, the question then is, if we train local LMS only on well-verified domain data, we will get still hallucinations, which is, I mean, this was touched a bit also by Yuan-Sen, I would say, in your talk. So, but I don't know if you have, if you want to contribute, if you want to say about this, or how much the training and curing the training will help us to avoid or stay away from hallucinations. So I don't know if someone wants to answer, to comment. Paula?
Yeah, regarding the first point, I think the problem is that normally the tools that are openly available for the community are designed to always provide an answer. But from our tests, when you give the prompt instruction, if you don't know the answer, say, I don't know. Okay. The LLM is able to say that. So I think it's most a matter of the companies that are behind these tools that are not, they don't want the users to get an answer that is, I don't know. But you can modify that if you have control on the tool. At least from our experience, that's what we are trying to do. Okay, I see. Okay. So it's a fine-tuning beyond the machinery, basically. Or... Yeah, it's basically giving instruction. And also you can regulate this parameter that is called temperature, where you allow like some freedom to the LLM to invent things. And that's why we are testing this in-house model, because we can have control on all of these aspects. While if you use ChatGPT or Gemini, you don't have that control. Okay, I see. And Yuan-Sen, you wanted to add something?
Right. So yes, I show you in the plot, right? So the proprietary models, or the big models, is doing pretty well. And one thing I didn't mention is that for the pre-training, the CPT models, the continual pre-train on astronomy, like even though we can like improve on the score, it's really hard to maintain the calibration of the confidence. Just like when you are just keep like training on the astronomy journals, you seem to like lose sight on how good or bad you are, which is also quite aligned with the sort of how human behave, and that is the tough part, right? So this is why like doing the pre-training and the fine-tuning on the model seems to be, like, at this point, not really that worth it. It's a very academic like inquiry, but for real like performance, because like you lose the calibrations, and they're pretty hard to recover.
Okay. So I have maybe it's really, I mean, we are chatting, right? So it's a kind of a provocative question to say. But so I'm an astronomer, and today is the day. Today we are discussing using AI in astronomy, right? Or GPT LLM model in astronomy. So yesterday maybe if you have a chance, you can watch the talks again. But basically, what I got from computer scientists, okay, is that, and also discussing with colleagues, is that we are in an era where basically we are struggling understanding what really, once you train an LLM model, then it's struggling to understand what's happening. Basically, when making a question and it gives us some result, it's kind of mystery to a level that the computer scientists are a lot testing the facility to see which biases they are, how the accuracy, so now as an astronomer, how do we, again, I mean, this is against trust, but I mean, so on one side, if I see, for example, an application for archive like it was shown today, I think that's fantastic. Or is an advanced research engine that you can use to search for every, I don't know, spectra that's been taken for a galaxy or whatever. So that's very convenient. But if you want to have an astrophysical reply or an astrophysical interpretation or analysis, that's, I don't know, then knowing that the computer sciences are a bit concerned, I would say, aren't we also concerned a bit? I don't know. You see, so if you, yeah, Christopher?
So a couple of comments. I think let's take the medical applications as an example just really quickly. The United States healthcare system is not a wonderful thing, but I think if you realize that the fourth leading cause of death in hospitals in the US is physician error, artificial intelligence systems don't need to be perfect to be useful. And I think it's important that we benchmark these against realistic comparisons. All that training data in those AstroPH papers, I have news for you guys. Not all those AstroPH papers are correct. People hallucinate too. So I do think it's important that we have sort of realistic benchmarks. Point number two, as Yuan-Sen emphasized, these systems are changing fast. The LLM systems that we're working with right now are the worst we're ever going to see, and they're only going to get better, and they're getting better really, really fast. So I don't think we should dismiss things out of hand on the basis of current limitations. I'm not suggesting you're doing that, but I think when we do these sort of comparisons, oh my God, they hallucinate, it might tell me something that's wrong. Even my Harvard colleagues have occasionally told me things that are wrong. I know that's a hard confession, but there you go.
It's true, but it's a good point, of course. But there is a level of in a sense, there is always something that for me is precious, which is the relationship between the fact that you when you talk to a person, there is some, I mean, if you ask something to a colleague, the colleague give you an answer, there is a relationship between, taking the responsibility of what the person says, so you can, in a sense, it's different than the machine that doesn't have any responsibility, because the machine is a machine, right?
And I'll yield the floor. I think one thing that's pretty clear to us is it's the product of domain expertise and these tools that equals success. And one of them does not substitute for the other. And second, everybody has to take ownership and responsibility for things that they put forth, regardless of what tools they turn to generate whatever information they think they're purveying.
Yeah, that's a good point. Yes. I think there was Yuan-Sen first, and then Merlin.
Yeah, I think the situation is very similar to self driving, but also with slightly less implication, because like no one dies here, and of course you need to take the responsibility, and it also depends on what comfort level you are, right? So for example, I am a pretty bad driver. I will take self-driving like any moment of the time, because the chances that I kill myself is higher than self-driving. But if you are a very good driver, sure, right? You want to steer the wheels. And in my daily research, of course, there are tasks that I trust myself more, like coming out with really complex plan. In fact, like most of the PhD thesis that I assign my student cannot be solved by O1 still. So it's really about your comfort level. I think all people have to decide what you want to do with that, and no one dies, and you have to be responsible for what you wrote in and put on archive.
Yes, indeed. Thank you. I would like to hear Nolan, so you can give an early, I would say, sorry, an early career scientist, I would say, perspective on the use of these tools, in fact.
Yeah, yeah, pretty much similar to what Yuan-Sen and Christopher was talking about, is that if they're useful, we should use them. You don't really need to understand the internals of your colleague's brain to have them, to work with them, really. So unless we're trying to, I know like these companies like Anthropic are looking in the internals at the neurons in order to try and improve the model. And that would be useful to understand these systems. But as astronomers, unless we want to switch to computer science, then I think it's fine if we don't really know what's going on, because in the end, they do astronomy the same way we do, which is writing code and describing their methods and deriving equations. So as long as we have a really solid peer review, I think this will be really great for astronomy. And if we automate peer review, which I've also heard about, then I think that would be a bad idea. Because then you just have garbage creation. But yeah, peer review is going to have to get really strong when we start getting like AI generated papers. Yeah.
Okay, I think tomorrow maybe I can invite you all to attend the talk for tomorrow, because tomorrow we will go also a bit in cognitive science, so to understand a bit better from cognitive psychology to which extent the use of such tools have an impact also on our capability to learn, and so the capability also to do a solid peer review, as you were mentioning. That's what I was thinking. So to do a good peer review, you need knowledge, and knowledge needs, still you need to read and basically digest information, not only have information, but digest them, understand them. And so so learning is still something that requires some sacrifice. And so it would be interesting to see whether AI is making this in danger somehow, okay, by speeding up the processes, everything, by speeding up everything. Unless there are other questions, because I have.
Can I make a comment?
Oh, absolutely. Sorry, I didn't. Sorry, Maggie, I didn't see you then. Sorry, so sorry.
It's okay. Kind of following on this. So everyone's talked about, okay, what if the AI makes a small mistake or things like that and hallucinations? That's fine. But when we actually get to the level that humans are purposely making these like incorrect things using AI, and that could be really problematic for us. And like some kind of example I can see of that in astronomy is we're all fighting for research grants. And so you want your like research to come across as the most exciting, state of the art and things. So you could get AI to create kind of this situation where everything you're doing is solid. It could be completely fake, but your AI could help you create a quite compelling case. And that's quite scary. And even without AI, we have examples of, I hate name dropping, but for example, like Oumuamua, when people were saying, oh, that's an alien spacecraft, so that they could get more grants and kind of taking that away. It can be a really bad thing as well, not just, okay, the AI makes some mistakes, we can disclude them. But what if people are actually using it to make purposely these mistakes? That could be a really bad thing.
I agree that on the fact that it's that's why we have, I'm sorry to go back to that, the way we have in the program that on Thursday we will go specifically to the impact on writing, I mean on basically on how you say, on writing proposal or writing application, on evaluating those, because as you said, the impact would be huge. It's huge even today. How we have okay, Andreas.
Okay, slightly different topic, but we have heard a lot about benchmarking and right and wrong. In many cases in physics, it's not about right and wrong, but about the right level of approximation. For instance, talking about, say, the orbit of the Earth, in one context, it's perfectly fine to assume that it's circular. In another context, I may need to take into account that it's an ellipse. And if I need to be precise, I have to take the JPL ephemeris to take into account disturbances by Jupiter and Saturn and so on. So part of my expertise as a trained scientist is knowing which level of approximation is appropriate in which context. Do I need to include friction? Can I neglect it? If I do orbital integration, do I need to take into account tidal effects? Do I need to do relativistic corrections? All these things are part of what the toolbox of a trained physicist contains. So my question is, in general, how is this taken into account in these large language models, or can it be taken into account, and how do I prevent things from the wrong level of approximation creeping in and disturbing my desired answer by either being overly complicated and expensive or being overly simplistic and inaccurate?
Thank you. I see. Thank you, Andreas, for the question. Merlin,
Yeah, I mean, I'm up for giving an answer. I'm a bit loath to answer these things because I'm an astronomer who was previously a particle physicist. I don't really have any expertise in the field, but I think I have some thoughts on it. And it's also thoughts that kind of relate to a lot of the other questions. And it also seems to be the approach that's being taken by OpenAI these days. So it seems like having multiple agents who are talking to each other can provide a lot of this. So having a chain of thought where one LLM agent is asking another LLM agent, oh, given this context, do you think what level of fidelity do you think is appropriate, is a kind of way of using the model's intelligence to make sure that it does things at that correct level. And it's kind of necessary because you can't necessarily put everything that you need into a system prompt because you don't know what you're going to be asked. You don't know what kind of pre-prompting is necessary, but you can have a kind of a monitoring oversight agent saying, oh, well, when you get a question like this, think it through and think about the necessary levels and then check that things are going correctly. And this kind of approach is also useful. People were talking about, confidence levels of, oh, don't answer the question if you think your confidence level is only 5%. That's an intrinsic problem with LLMs, because if you actually look at what they're doing, they're talking about their confidence level of the next token, but the next token is a word or a fraction of a word. So to say, what is your confidence in the statement overall is not something that the LLM itself is necessarily able to assess, but you can have an agent that looks at the output that is the response and says, oh, what do you think the chances of that being correct are, to look at it as a whole, which then actually kind of gives you this emergence of kind of intelligence in some way, in a way that the actual model, as it goes about predicting with extreme confidence, the individual tokens can't actually assess like whether or not it's a good answer or not. And this is sort of more the O1 avenue where you've got internal thought processes, and I'm sure internally there are a bunch of different agents all having conversations internally, and that's what gives you this kind of chain of thought reasoning. So I think that approach is looking increasingly promising.
Okay. Yes. Yuan-Sen first, and then Paula.
Yeah, I also argue that O1 is not just doing the chain of thoughts, but it's also the training on that, right? So it's really a reinforcement of learning. And lots of things that Merlin mentioned is actually are implemented in Mephisto. So like how we do that is like once you have done the tree of thoughts, then you have an agent that will summarize that. But then you will also break them down into a logical expression, meaning that for this chain of action, can I really pin down what are the modular changes, and then we validate the knowledge. So now you know that I have changed the dust models. When I see X, I do Y. Then we will go on to test on the validation set to test on a random set to see if this knowledge is useful or not. And this but also what is being done in O1. If you look at, like, ask them to solve a PDE, then you can see they are really making approximation. And they know how to make approximation because they have run through this many, like, tree of thoughts and have validate by themselves what works and what do not works.
Paula?
Yeah, I just want to follow on what Merlin was saying, because that's exactly what we have been doing in our experiments at ESO. And in this context where the problem is very, like, specific for the task of supporting users of ESO instruments, very small models can easily identify answers that are totally wrong. I'm running this in my lab, but, like, you don't need very, like, the state of the art to solve this problem when the task is simple. Like, if you want some tool that is going to solve every single problem in astronomy, then maybe yes, you need a very large model. But for a very specific task, you can work with very small models.
Yes, indeed, I understand. For fine-tuning basically to smaller tasks. Yeah, but I actually, it's for me, it's a concept that I wasn't completely unaware of. So the fact that you can have these different how you call them, agent to work in parallel, basically. So can you, I mean, some of you, can you give me an example? So really, I didn't know that. How does it work? I mean, just briefly, just to give a sense of Yuan-Sen, yeah, of course.
Yeah, I think the key is just to break down the question, right? So since we are not in AGI yet, right? So ideally, I want to give a prompt and then that will run by its own. But most of the tasks, even for SCD fitting, there are different steps, and different steps are required different specification. You can think about the one that the proposal actions requires some RAG, right? And the one that write the code need to have extensive prompting to know what's wrong and what's do not wrong. So in the end, you are just using the same copy, but you are really doing a combination of prompting and fine-tuning and RAG to make sure that you break down the question easy enough for the LLM to handle.
I see. So you work by topics, basically, or breaking down the problems in sub-problems. So, Paula, yes?
Yeah, maybe I can use as an example what we have been doing with Claudio. So basically, in this context, we want to help users find the information in the manuals and the website. So what we do first is we have a model that is first grading the documents that are relevant for the question. Then you generate an answer from this, and then you ask another model, another LLM, are these answer and documents related? Yes or no? Then the flow continues. So at the end, it's just having small models testing or checking what the others were doing. So it's a chain of checks. But these models are independent. So it's not the same model that generated the answer, the one that checks. So at the end is basically this, like having different agents, like these models, checking what is doing the other without having any interaction between them.
Okay.
That's the approach we're using, but maybe there are others. I think that's, well, we don't have yet more sophisticated tools like the ones that O1 are using with, I forgot the word. Sorry. But yeah, it's at the moment we're not using any specific way of training. It's just using the models as they are.
Okay. Thank you, Paula. Thank you. I have a bit of a visionary question. Is particularly for Maggie, maybe, because you mentioned that the astronomer the AI astronomer, right? You mentioned this identity, right? This in the future. So I was wondering, have you ever done the exercise? So given the fact that the speed on which these LLM models are performing and are becoming more and more efficient, in 40 years, in 50 years from now, will be really, so what was going to be our job as an astronomer? So
with all the LLM models that I've found so far, they seem to be able to do quite simplistic things. And that will take away a lot of kind of like our master students, maybe, PhD students, maybe, a lot of the kind of low level things, because kind of not talking about O1 at the moment, but like all the previous models, they're largely just based on probability. So they're looking at, even when you take into temperature, they're looking at what's most probable to solve these problems. So even though we can say that there is some degree of creativity, they're still using what they've known, and they're not connecting dots between things like us humans do and have aha moments. So I think 50 years from now, we will still have astronomers that are experts and are coming with these grand new things, new ideas. And I think kind of the lower level astronomers will kind of disappear. The ones, that are tuning out 10 papers a month, doing exactly the same thing on a different data set, pretty much. I think that's where we'll be.
I see. So, well, I'm a low-level astronomer, so I will disappear. That's for sure. So, Nolan?
Yeah, I'm in my second year of grad school, so hopefully I get out of it. Yeah, I think I have a slightly different point of view in that I think what these models are, it might be too optimistic, but I think in the near term, these models are going to do the technical tasks extremely well. They're obviously amazing at like using like CUDA and PyTorch and all these, and they even can do ADQL to query Gaia and all these small technical skills that a master's or a PhD or even a professor would have to read up on a ton of documentation to really master. These models can just read it, and you can ask what you want, and it'll do it. So I think that we might be limited not by our technical skills in the future, but really by our imagination, I would say, and we would be tackling the harder problems as PhD students, as master's students, because we'll have all these tools under us, so we'll just be that much more productive. We'll have our own team of these AI agents, and so we can focus on the bigger picture rather than formatting our plots to look pretty and spending hours doing that. So I hope that's the future for grad students, at least.
I see. I just wanted to, I understand. I just wanted to, maybe my perspective is that there is still, I think, but tomorrow maybe we'll discuss a bit more about that, but there is still a value, even in doing the frustrating exercise to go through a long text, finding information, and because it is, for me, for example, that I have not particularly gift mind, so when I go through it, I stimulate my neurons, so I see that so the learning, in a sense, what I get back, it's something that goes beyond just a result. It goes into my growing, me becoming more human, me experiencing, achieving knowledge. So there is a beauty in that. So I just wanted to say that. I'm not saying. Merlin first, and then Marcos.
So, I was just going to say, the iPhone is less than 17 years old. ChatGPT is not yet 2. If you think you can predict 30 or 40 years in the future at this point, and this is not a positive or a negative prediction, right? It's just saying that extrapolating from a curve of this shape is like an absolute fool's errand. If anyone's seen the movie, like the computer generated movie of Will Smith eating spaghetti and saying we'll never have text to video, and then looks at Sora like a year later, 30 or 40 years in the future, I mean, who knows? But I think Chris said the important thing in the comments, which is, will AI put astronomers out of business? No, but astronomers who use AI will put ones out of business who don't. I mean, that's got to be clear. So pick up the tools and start running with them. Where we will end up, I have absolutely no idea. I just know that I won't have an idea until it's happening.
I see. Yeah, I understand. Yeah. Marcos first, and Maggie.
Yes. So although I quite agree that many of the tasks that we did as PhD students and maybe young postdocs can be done with one of these agents, like the click of a button. There is also some value in all of that. So maybe part of the creativity that we may have now is a result of experience struggling with things and dealing with problems and trying to understand things. So I'm very happy that the new graduate students don't have to deal with silly things like making pretty plots. But I think there was also a value in struggling with problems. This will, but I think that the good thing is that the younger generations now they can focus on the actual scientific problem and like put aside all this technology related things that would take up a lot of your time during your PhD and your postdocs. So I think we are getting better, I think.
Yes. Thank you. Thanks, Marcus. Maggie?
Just making a comment on what you said. If we go back like 20 years, maybe 30 years, like if we wanted to know something, you would have to go out of your way, go to a library and look it up in a book. But now you head to Google. It doesn't mean that all libraries are closed and no one enters them anymore or anyone picks up a book anymore. Like we still do that, but it's just more efficient to just head to Google. So I don't think it will be completely erase out all the kind of mundane little things. People might still do them for fun. But I don't think, I think what Nolan said, like it will like remove the, make it more efficient to not do those things if you don't want to.
No, I completely agree. I completely agree. But I absolutely. But the exercise, which even this, it's difficult to predict what it will be, because I think it's good to. It's clear that this technology is happening. I am very fascinated by technology in general. So I love to see this. I want to understand, and it cannot be stopped. I mean, so we need to live with this and collaborate with this. But just the effort, I think, is not wasted time to do an effort by trying to understand what the consequence will be, in a sense, somehow. Because it's true that Google, as you said, the search engine allows you now to browse literature more efficiently than going to a library and having to go to books. But the speed on which this is happening now, I felt it goes beyond our capability to digest information anyway. So it's going so fast now but our brain is not that fast anymore. So it's still so I don't know. I'm always afraid of the speed of which things are happening and the speed of which information is going out and our capability to process that we as human is still the same, more or less. So, you see what I mean? So, but okay, sorry, maybe Yuan-Sen?
Right. I'm a self-proclaimed like AI optimist. You think about when in three-body problem, I will be welcoming other scientists to come. But I think there are few problems here, right? So one thing is the human will still be working. Like, I feel like I have like improving my productivity like twofold like each year for the last 3 years. But I don't have like 8 times more free times, right? I still work all the time. And that is like a reshuffling. So people who know how to use AI effectively will have 8-fold the productivity than the people that don't use that. So it become like ability of like how well like you can use AI. And I don't think like that will still put people out of job, because like you would just select people who know how to use like AI well. What I think would be problematic, which I have like deep the discussion with colleagues, is like even I myself like sometimes I start to debate like should I use my grant for grad students. Also, I use my grant for API. And that is true, right? So you think about in the grant, limited limit, the calculation is very different. So when I pick up a PhD student now, I have a very clear mind that I am doing that for education. I know that the amount of money, like even not now, like in the near future, in terms of the scientific output, is not as important. And in education, like this is a very interesting balance, because like if you go to industry, like people will just lay off people, right? Because their calculation is to maximize the profit. But the education system is more than just maximizing the science. So a part of science is to do the education. And now you have this, it used to be more aligned, you know, the more students that you have more output. And these two go now start to bifurcate. And all people like need to think about what is the purpose of a university, like what's the purpose of like ESA? Is it like maximizing the science or maximizing the education? And what is the right combination of both?
Thank you. Yes, Paula.
Yeah, maybe I can give an example of my own experience. So when I started my PhD almost 11 years ago, my first project was to select by eye, looking at high resolution spectra from US, magnesium-2 absorbers in like several hundreds spectra. It was a tedious job. And at the end, I think in 1 year, I was only doing that. I didn't have time to do any like astrophysics. I just was looking for these observers. Now there is a student that is coming to work with me and Celine on using AI to do this with millions of spectra from foremost. And the student will be able to do science, astrophysics with the result. So I think we need to think that these tools are not gonna like replace us. It's just a tool that will help us to be more productive, to do actual astrophysics and not waste our time in like doing stupid things just by looking by eye, where are, I don't know, magnesium-2 observers. So I think we need to be more positive, but also understand the limitations. And I think I personally don't like these formulas that are like one problem, like any problem can be solved by one general model. Because in experience, at least I know we're not there. It's better to have models that are more personalized for a different, like a specific task. Because when you see these general applications, they tend to fail because of the same reason. They're too general. And my final point is like, maybe this is a positive thing, the fact that we will have these tools to help us, because I think now we have the problem that we rely a lot on PhD students, and we end up with several PhDs without jobs. Maybe now we will have tools to help us, and we don't need to rely on having 5 PhD students to do some very simple tasks that can be done with an AI. Because the market now is populated with PhDs without jobs, and I don't know, maybe this is the solution. When I was finishing my PhD, I was super afraid that the number of astronomers around is so huge, and the number of jobs around are very, very few. Maybe it's a positive way. It's positive that now we don't need many grad students to do science, because at the end they can dedicate their time to other more useful tasks. I know it's controversial, but
yes, very okay. Thank you very much, Paula. Christopher, please.
So I would associate myself with Yuan-Sen and say I'm an optimist here. And the point I want to make is currently these AI tools have a highly variable amount of effectiveness. There's a very sort of jagged edge of where they're useful and where they're not terribly capable. And I think what we're going to find as things evolve is the question is going to be, how can we bring these tools to bear on what we're all trying to do to make ourselves more efficient, more productive, and more cost-effective, right? And I think it behooves us all to stay abreast of what things they're good at and what things they're not good at. And, you know, as a geezer guy who, actually speaks a little bit of Fortran, my ability to do things in Python has gotten 10 times better. No exaggeration, factor of 10 increase in productivity by harnessing these tools and bringing them to bear on generation of code. Now, is all the code flawless? No, but I actually know enough to know how to edit it and make it work right and do what I want. So I just don't have to struggle as much with Python syntax anymore and zero-based indices and stuff like that. So, but I think that's going to be a dynamic landscape. And on the educational side, I do think Yuan-Sen also put his finger on something, and that is, how is that going to evolve? How do we serve the undergraduates? How do we use these tools to teach people better? And how do we teach people to be proficient and ethical users of these tools? I think that's the challenge in higher education.
Yeah. Thank you, Christopher. Fabio?
I think you all touched the topics. It's very interesting. So I'm a software developer, so I'm one who should be afraid of losing jobs, but I'm not. To talk about the new tool, you don't know what's inside. I can tell you that when I started studying, there were all professors who didn't trust the microprocessors. And they were doing all the calculation with logarithmic tables and rulers. And sometimes they were right because the machine was making mistakes. At that time, we called them bugs. Now, these mistakes, we call them hallucinations. So I see all this stuff as a tool to do more interesting things. Probably in a short time, I will stop coding. I will do something else, like, for example, talking to the customers, collecting requirements, and writing user stories. By the way, a language model is perfect to write user stories. It does it much better than me, but it's not able to capture the domain, the will of the customer, of the human beings. So we are not there yet. To see in the future. So I'm one of the guys who challenged you, Giacomo, at lunchtime. As was mentioned, it's very difficult to look into the future. I just remind that no science fiction writers in the 50s, 60s, 70s mentioned internet, none of them. So it's rather difficult, impossible to look into the future. But it was mentioned, I think, in the chat, what can be foreseen is a new way to do things, and particularly do science. For example, imagine if tomorrow the new astronomer would need a lot of skills, like in different disciplines, like astrophysics, but also biology, chemistry, and engineering. Would you be able to do that, to gain all these skills in a lifetime? I don't think so. So maybe these tools can be a way to gather these skills in a wider range of the human knowledge to discover new things.
Yeah, I understand. No, I agree. I completely agree. Yeah, for me, the big issue, the problem in predicting what's going to happen, that we all somehow grow in a classical educational environment, in a sense. There will be in 2 or 3 generations, maybe the educational environment will change, and then we will, I don't know how different things will be. So sorry, we are basically coming to an end, I would say. But I will take the chance as a chair of today. I have a curiosity and I cannot resist to make this question. I'm sorry, it's really very technical, but it's related. Probably it's more for Christopher and Merlin, but maybe everyone is welcome to. So it's about telescope operations in particular. And I was wondering, because it's a curiosity, maybe it's completely nonsense, but do you think, for example, one of the big problems from ground-based astronomy is that is the atmosphere, right? So we are happy that there is an atmosphere, of course, but it's a problem, right, for us. So we have this, wavefront sensor, Shaka-Hartmann, all these complex AO systems. So given the forecasting capability that you, Christopher, that were mentioning, we will be able at some point to have a system that predicts the optimal mirror shape and based on the basically trained algorithm able to understand that, the fluctuation of the atmosphere and shaping. So an active AO system basically fully run by a machine learning or whatever tool, basically, instead of having a waveform sensor.
So two quick answers. One is friends at CFHT, there's a good paper on using machine learning methods generally to optimize the airflow in the dome to suppress dome seeing. And that's a complicated multi-factor problem. And they show some good success with that. I think if your question is, will we have the ability to sort of forward predict atmospheric turbulence and compensate for that? My short answer is no. I think that's a chaotic turbulent system, and we have to do that in real time.
I see.
So deterministic, yeah, truly chaotic and turbulent things, less so.
Okay, I see it. Merlin?
I was just going to say that I think the active optics control system for Rubin, is a problem that is absolutely brilliantly suited to more traditional ML stuff. And I don't see a route to like throwing that at an LLM because it's just kind of the wrong tool for the job. But a kind of having an LLM help you, handcraft your traditional ML approach to optimizing that control space is absolutely something that could be done. And it is perfect for ML. And actually, it's a very hard problem without machine learning. So it's perfect for this, but maybe not generative AI as such.
No, I was thinking more in adaptive optics more than active optics as such, because they're, yeah.
I'll say it this way. Pretend like you have an AO system that has 10 adjustable parameters. I could imagine embedding that process in an outer loop where an LLM system optimizes a complicated thing on your behalf, which is, I think, kind of what Merlin was getting at.
Okay, so, okay, good. So I would like to, maybe we can now close the session to today. It's been really a big pleasure. I would like, because I saw there was a post of Sandra. Sandra, I don't know if you feel okay to talk. I just wanted to ask you because tomorrow we will have a full session. So maybe you can make a big spoiler just to tell us a bit about tomorrow and please, yes, and your point that you made actually.
Yeah, thank you. Yeah, so I'm a psychologist and I'm a researcher in psychology. I have no clue about astronomy, but I do think that with this AI and large language model topic, we have a big overlap, and this has become a big research topic in cognitive psychology specifically. And tomorrow we will have 2 invited talks by cognitive psychologists, Patrick Weiss and Ella Glickson. And I think they will tackle some of the points that were raised also in the chat here, where it was discussed which skills kids would have and which they won't have. We will not tackle all of this. I think for many points that were raised in the chat, there is no answer yet from psychological side, but we can discuss more about that tomorrow. But what we will definitely tackle in Patrick's talk is how we as humans use AI tools, for instance, but also other tools such as our smartphones to extend our cognition and to supplement our abilities. And then Ella will more tackle the topic of trust that I think was also mentioned in the discussion today. So how can we gain trust in those technologies? What is an appropriate amount of trust? How can we calibrate this trust? And I think, then we will have of course, still many open questions that we can discuss together and bring this expertise and overlap between astronomy and psychology together.
Very good. Thank you very much. Looking forward for tomorrow, really. Thank you, Sandra. So see you tomorrow, I guess. And thank you to everyone. I know you all are in different time zones, and it's been a big effort to stay with us. So I want to thank you, each of you. Thank you very much. It was very nice today. And as I said, the recording will stay on YouTube. I already posted the one of yesterday, so there is a dedicated playlist, and there I will put also the event of today. With this, we can close. Thank you to everyone, and see you tomorrow. Bye bye.
Thank you.
Thank you. Bye.
Bye.